in the vast expanse of space, light travels at an incredible speed of 299,792,458 meters per second. This cosmic messenger has been racing through the universe for billions of years, carrying information from distant stars to our eyes, allowing us to see the world around us. But what if we could do the impossible? What if we could reach out and stop light itself, freezing it in place like a photograph suspended in time? Tonight, we embark on a journey through one of the most fascinating questions in physics. If you could stop light completely, would you also freeze time itself? Or would the universe continue its eternal dance, indifferent to our cosmic intervention? This question touches the very heart of reality, challenging our understanding of the fundamental forces that govern everything we know. Light is not just the fastest thing in our universe. It is also the thread that weaves together the fabric of space and time. When Einstein revealed his theories of relativity over a century ago, he showed us that light speed is not just a measurement, it is a cosmic speed limit that shapes the very nature of existence. Time itself flows differently depending on how fast you move through space, and at the center of this cosmic relationship sits light, unchanging and absolute. But what makes light so special? Why does this invisible force hold such power over time? As photons race through the void, they carry more than just energy. They carry the very structure of reality itself. Every moment we experience, every second that ticks by, is intimately connected to the movement of light through space. When you look at a star in the night sky, you are not seeing it as it is now, but as it was years ago when its light began its journey to your eyes. This creates a beautiful paradox. We live in a universe where the present moment is constantly being redefined by light from the past. The sun you see shining is actually the sun as it was 8 minutes ago. The moon glowing softly in the night sky shows you its face from just over a second in the past. Even the person sitting next to you is revealed to your eyes by light that took a tiny fraction of a second to travel from them to you. Now imagine if we could stop this cosmic messenger. Picture a universe where photons hang motionless in space, suspended like frozen raindrops. Would this act of stopping light create a kind of temporal prison where time itself becomes trapped? Or would time continue to flow, leaving us in a dark universe where only touch and sound remain to tell us that existence continues? The relationship between light and time runs deeper than most people realize. In the quantum world, where particles dance in ways that defy common sense, light plays a crucial role in the very measurement of time. Atomic clocks, the most precise timekeepers ever created, rely on the vibrations of atoms as they interact with light. Without light, could these fundamental processes continue? Could time itself be measured? Some scientists believe that stopping light would create effects beyond our wildest imagination. Others argue that time is independent of light, that the universe would continue its expansion and the dance of particles would go on, even in a world of eternal darkness. The truth may be stranger than either possibility. As we explore this question together, we will journey through the mysteries of relativity, dive into the quantum realm where reality becomes fluid, and peer into the heart of black holes where light itself cannot escape. We will discover how light shapes not just what we see, but how we experience the passage of time itself. The universe holds many secrets, and tonight we chase one of the most profound. In a cosmos where light defines the possible and time marks the rhythm of existence, what would happen if we could stop the music? Would the dancers freeze in place, or would they continue their eternal waltz in silence? Let us begin this exploration together, following the path of light through space and time, seeking answers to questions that have puzzled humanity since we first looked up at the stars and wondered about our place in the infinite cosmos. The speed of light is not just fast, it is the ultimate speed limit of our universe. At exactly 299,792,458 meters per second in a perfect vacuum, light moves faster than anything else we know. To put this incredible speed into perspective, light could circle the entire Earth over 7 times in just 1 second. It could travel from New York to London in about 20 milliseconds, faster than you could blink your eyes. But why does light travel at this specific speed, and why does nothing else in the universe move faster? The answer lies deep within the fundamental structure of reality itself. Light speed is not just a property of light, it is a property of space-time, the very fabric from which our universe is woven. This cosmic speed limit was built into the universe from the moment of the Big Bang, establishing the rules by which all matter and energy must play. When Albert Einstein first proposed his special theory of relativity in 1905, he revealed something extraordinary about light speed. He showed that this velocity is constant for all observers, regardless of how fast they themselves are moving. Imagine you are on a train traveling at 100 kilometers per hour, and you shine a flashlight forward. You might expect the light to travel at light speed plus 100 kilometers per hour in the forward direction. But Einstein showed us that this is not what happens. The light still travels at exactly light speed, no faster, no slower. This strange behavior of light reveals something profound about the nature of time itself. As objects approach light speed, time begins to slow down relative to stationary observers. A clock on a spacecraft traveling at 90% of light speed would tick much more slowly than an identical clock sitting on Earth. If that spacecraft could somehow reach light speed, time would effectively stop for the travelers aboard, though they would never experience this stopping themselves. This relationship between light speed and time is not just theoretical. We see evidence of it everywhere in our universe. Particles created in the upper atmosphere by cosmic rays should decay long before reaching Earth's surface, yet we detect them regularly because time dilation allows them to survive their journey. GPS satellites orbiting our planet must constantly adjust their clocks because time moves slightly faster in their weaker gravitational field and at their orbital velocity. The speed of light also defines how we measure distances in space. When astronomers say a star is 100 light-years away, they mean it takes light 100 years to travel from that star to us. This creates a fascinating connection between space and time. Distance in space becomes time for light to travel, linking these two fundamental dimensions in ways that seemed impossible before Einstein. Consider what this means for our experience of the universe. When you look at the sun, you are seeing it as it was 8 minutes and 20 seconds ago, because that is how long its light takes to reach Earth. The nearest star beyond our solar system, Proxima Centauri, appears to us as it was 4 years and 3 months in the past. The beautiful Andromeda Galaxy, visible to the naked eye on dark nights, shows us how it looked 2.5 million years ago, when early human ancestors first walked the African savanna. This delay in light travel creates what scientists call our light cone, the boundary of what we can possibly know about the universe at any given moment. Events happening right now on distant worlds cannot affect us until their light has time to reach us. In a very real sense, the speed of light determines the rate at which information can flow through the universe, setting the tempo for cause and effect on cosmic scales. But what would happen if we could change this fundamental speed? What if light could be slowed down or, more dramatically, stopped completely? Some scientists have actually managed to slow light down in laboratory conditions, using specially prepared materials that interact with photons in unusual ways. In these experiments, light that normally travels at 300,000 kilometers per second can be reduced to the speed of a bicycle, or even brought temporarily to a complete stop. These experiments hint at the deep connection between light and the flow of time. When light is slowed in these materials, the very atoms that slow it experience time differently. The electrons in those atoms vibrate at altered rates, their internal clocks seeming to tick out of sync with the rest of the universe. This suggests that stopping light might indeed have profound effects on the passage of time itself. The implications become even more intriguing when we consider that light is not just electromagnetic radiation, it is also the force that holds atoms together and governs chemical reactions. Every biological process, from the beating of your heart to the firing of neurons in your brain, depends on electromagnetic forces mediated by photons. If light were truly stopped everywhere, would these fundamental processes cease as well? Light also carries momentum despite having no mass. When sunlight hits a surface, it exerts a tiny but measurable pressure. Solar sails, proposed for future space missions, would use this light pressure to propel spacecraft across the solar system. If light were stopped, this momentum would vanish, potentially affecting everything from the orbits of planets to the behavior of gas clouds in space. The speed of light is intimately connected to other fundamental constants of nature. It relates to the strength of electric and magnetic forces, the mass of particles, and the expansion rate of the universe itself. Changing light speed would ripple through all of physics, potentially altering the very laws that govern reality. The atoms in your body, held together by electromagnetic forces, might behave differently in a universe where light speed could be manipulated. Perhaps most mysteriously, the speed of light appears to be connected to the arrow of time itself. Time always flows forward, never backward, and this direction seems linked to the way light and information propagate through space. Cause always precedes effect because information cannot travel faster than light. If we could stop light, would we also stop the forward flow of time, creating a universe frozen in an eternal present? As we contemplate these possibilities, we begin to see that light is not just the fastest thing in the universe, it is the conductor of the cosmic orchestra, setting the rhythm by which all of reality dances. The speed of light defines not just how fast things can move, but how quickly change itself can propagate through the fabric of space-time. In stopping light, we might not just freeze illumination, we might freeze change itself, creating a universe where nothing can happen because nothing can influence anything else. This fundamental connection between light and time extends to the very structure of matter itself. Every atom in your body contains electrons that orbit nuclei at specific energy levels, and these electrons can only change levels by absorbing or emitting photons of light. The stability of matter, the colors we see, and even the chemical reactions that power life all depend on these interactions between matter and light. If light were stopped, would atoms themselves become unstable? Would the electrons freeze in their orbits, unable to absorb or emit the photons they need to maintain their quantum states? The mystery deepens when we consider that light is not just electromagnetic radiation traveling through space. It is also the mediator of one of the four fundamental forces of nature. The electromagnetic force, carried by photons, is responsible for virtually everything we experience in daily life. It holds molecules together, creates the friction that lets us walk, generates the electrical signals in our nervous system, and powers the nuclear fusion reactions in stars. Without light, without photons to carry electromagnetic force, the very structure of reality might collapse. Consider the profound implications for time measurement itself. Our most precise atomic clocks work by counting the vibrations of atoms as they transition between energy states, absorbing and emitting photons at incredibly regular intervals. The cesium atomic clock, which defines our standard second, counts exactly 9,192,631,770 vibrations of a cesium atom. Each of these vibrations involves the interaction of the atom with electromagnetic radiation. If light were stopped, these atomic transitions might cease, leaving us without any way to measure the passage of time with precision. But perhaps time would continue to flow in ways we cannot perceive or measure. The weak nuclear force and the strong nuclear force, the other fundamental forces besides electromagnetism and gravity, do not depend directly on photons. Radioactive decay would likely continue, particles would still interact through the strong force, and gravity would still warp space-time. In this scenario, stopping light might create a universe where time flows but cannot be observed or measured, where change occurs but cannot be seen or detected through electromagnetic means. The relationship between light speed and the expansion of the universe adds another layer to this puzzle. The cosmos itself is expanding at an accelerating rate, with distant galaxies moving away from us at speeds that approach light speed at the edge of the observable universe. This expansion is intimately connected to the fabric of space-time itself. If light were stopped, would the expansion of space continue? Would new regions of space-time continue to come into existence, even in a universe where electromagnetic radiation could not propagate? Scientists have discovered that the vacuum of space itself is not truly empty, but filled with quantum fluctuations, virtual particles that pop in and out of existence at timescales so brief they seem to violate conservation of energy. These quantum fluctuations include virtual photons, electromagnetic disturbances that exist for impossibly short moments before disappearing back into the vacuum. If light were stopped, would these quantum processes cease as well? Would the vacuum itself become truly empty for the first time since the Big Bang? The implications for black holes become particularly intriguing. These cosmic monsters trap light within their event horizons, creating regions where photons can never escape. Yet time continues to flow inside black holes, though it flows differently than in the rest of the universe. Near the event horizon, time dilation becomes so extreme that an outside observer would see time appear to stop for anything falling in. But for the falling observer, time continues normally even as they cross the point of no return. This suggests that time can flow even in regions where light cannot escape, hinting that stopping light universally might not necessarily stop time itself. The connection between light and information is equally profound. In our universe, information cannot travel faster than light, establishing what physicists call the speed of causality. This cosmic speed limit ensures that cause precedes effect and maintains the logical structure of reality. If light were stopped, information could no longer flow between distant points in space. Each region of the universe would become isolated, unable to influence or be influenced by events elsewhere. This might create a universe of frozen cause and effect, where each point in space exists in perfect isolation. Yet quantum mechanics suggests that some connections transcend the speed of light. Quantum entanglement allows particles to maintain instantaneous correlations across vast distances, seeming to violate the principle that nothing can travel faster than light. These quantum connections do not allow information to be transmitted faster than light, but they do suggest that the universe has hidden connections that operate outside the normal flow of electromagnetic radiation. If light were stopped, would these quantum correlations continue, maintaining some form of cosmic connectivity even in the absence of photons? The energy stored in electromagnetic fields throughout the universe is enormous. Every radio wave, every beam of sunlight, every photon from distant stars carries energy through space. This electromagnetic energy contributes to the total energy density of the universe and affects the rate of cosmic expansion through Einstein's equations of general relativity. If all this energy were suddenly removed by stopping light, the universe itself might begin to contract, reversing billions of years of expansion in a cosmic implosion. But perhaps the most profound question is whether consciousness itself depends on the flow of light and electromagnetic energy. Human awareness arises from electrical signals in the brain, neurons firing in complex patterns that somehow give rise to thoughts, memories, and the subjective experience of being alive. These neural signals are fundamentally electromagnetic phenomena depending on the movement of charged particles and the electric fields they create. If light were stopped, if electromagnetic forces ceased to operate, would consciousness itself cease to exist? Would the universe become not only dark, but also utterly devoid of any observer to witness its strange new state? As we contemplate these possibilities, we begin to realize that light is far more than just illumination racing through space. Light is the messenger that connects all parts of the universe, the force that holds matter together, the clock that measures time, and perhaps even the foundation of consciousness itself. In asking whether stopping light would freeze time, we are really asking about the deepest connections between matter, energy, space, and time. The answer may be that stopping light would not simply freeze time, but would fundamentally alter the very nature of existence, creating a universe so different from our own that the question of time itself might become meaningless. In such a reality, would time flow in ways we cannot imagine? Or would the very concept of temporal flow lose all significance in a cosmos where nothing can influence anything else? Light is not just fast, it is the very foundation of time itself. But if light was stopped, could the fundamental relationship between time and space be altered? Or would we discover that time has a deeper independence from the electromagnetic forces that seem to govern so much of our reality? Before Einstein revolutionized our understanding of reality, most people thought of space and time as completely separate things. Space was the stage upon which events unfolded, an unchanging backdrop that stretched infinitely in all directions. Time was the universal clock that ticked at the same rate everywhere, measuring the duration between events with perfect consistency. But Einstein showed us that this intuitive picture was fundamentally wrong. Space and time are not separate entities, but are woven together into a single fabric called space-time. This revelation came through Einstein's general theory of relativity, published in 1915, which described gravity not as a force pulling objects together, but as the curvature of space-time itself. Imagine space-time as a vast rubber sheet stretched tight across the cosmos. When you place a heavy ball on this sheet, it creates a depression, warping the surface around it. Smaller objects rolling nearby will naturally curve toward this depression, not because they are being pulled by a mysterious force, but because they are following the curved geometry of the sheet itself. In our universe, massive objects like stars and planets create similar depressions in space-time. The Sun creates a deep well in the fabric of reality, and Earth orbits around this well, not because it is being pulled by gravity, but because it is following the curved path that space-time dictates. Light, despite having no mass, must also follow these curves in space-time. When starlight passes near the Sun during a solar eclipse, we can observe it bending around our star, following the warped geometry of space and time. This curvature of space-time has profound implications for the flow of time itself. In regions where space-time is strongly curved, such as near massive objects, time flows more slowly compared to regions where space-time is relatively flat. This effect, called gravitational time dilation, means that a clock sitting on the surface of the Sun would tick noticeably slower than an identical clock floating in the empty space between galaxies. The difference is not merely theoretical, but has been measured with incredible precision using atomic clocks. Light plays a crucial role in revealing these distortions of space-time. When we observe light from distant objects, we are seeing not just their appearance, but also the effects of all the curved space-time the light has traveled through on its journey to us. Light from a galaxy billions of light years away has navigated through countless gravitational fields, each one slightly altering its path and the information it carries about time and space. The speed of light serves as the conversion factor between space and time in Einstein's equations. In the famous equation E equals mc squared, the c represents light speed, but this same constant appears throughout relativity as the fundamental exchange rate between spatial and temporal measurements. 1 second of time is equivalent to about 300,000 kilometers of space in the geometry of space-time. This means that light speed is not just the speed at which photons travel, it is the speed at which causality itself propagates through the universe. When we say that nothing can travel faster than light, we are really saying that nothing can travel faster than causality, faster than the rate at which cause and effect can spread through space-time. This cosmic speed limit maintains the logical structure of reality, ensuring that effects cannot precede their causes. Without this limit, the orderly flow of time could become scrambled, with events happening before their triggers, creating paradoxes that would tear apart the fabric of logical existence. The relationship between light and space-time becomes even more fascinating when we consider how light defines the geometry of space itself. The path that light takes through curved space-time is always the shortest possible route between 2 points, even when that path appears curved to us. Light follows what mathematicians call geodesics, the straightest possible lines in curved space. By observing how light travels, we can map the curvature of space-time throughout the universe, revealing the hidden architecture of reality. This connection between light and geometry extends to the expansion of the universe itself. As space expands, it stretches the wavelengths of light traveling through it, causing distant galaxies to appear redder than they actually are. This cosmic redshift provides us with a direct measurement of how space-time has expanded since the light began its journey. The most distant galaxies we can observe appear to us as they were over 13 billion years ago, when the universe was young and space-time was much more compressed than it is today. The cosmic microwave background radiation, the afterglow of the Big Bang, provides us with a snapshot of space-time when the universe was only about 380,000 years old. This ancient light has been traveling through expanding space-time for nearly 14 billion years, and its patterns reveal tiny fluctuations in the density of space and time that eventually grew to become galaxies, stars, and planets. In studying this primordial light, we are literally seeing the birth of space-time structure itself. But what would happen to this intricate relationship between light and space-time if light could be stopped? Would space-time continue to curve and flex, or would the geometry of reality freeze in place? The curvature of space-time is created by the presence of mass and energy, and light carries energy as it travels through space. If all light were stopped, a significant amount of energy would be removed from the universe, potentially altering the curvature of space-time itself. Consider the implications for black holes, those regions where space-time curvature becomes so extreme that not even light can escape. The event horizon of a black hole is defined as the boundary where light can no longer travel outward. If light throughout the universe was stopped, would event horizons lose their meaning? Would black holes still be black? Or would they become something entirely different in a universe where the concept of light speed no longer applied? The answer might depend on whether stopping light would affect only electromagnetic radiation or all forms of information transfer. Gravitational waves, ripples in space-time itself, travel at light speed, but are not electromagnetic in nature. These waves are created when massive objects accelerate through space-time, creating disturbances that propagate outward at the cosmic speed limit. If stopping light also stopped gravitational waves, then even the curvature of space-time might become frozen, unable to respond to changes in the distribution of matter and energy. Without gravitational waves to carry information about changes in mass distribution, distant parts of the universe might become gravitationally isolated from each other. A star that collapsed into a black hole would create gravitational effects that could never propagate beyond its immediate vicinity. the universe might fragment into countless isolated regions, each unaware of changes occurring elsewhere, each locked into its local configuration of space-time curvature. The quantum nature of space-time adds another layer of complexity to this puzzle. According to quantum field theory, space-time itself is subject to quantum fluctuations at the smallest scales. These fluctuations involve the creation and annihilation of virtual particles, including virtual photons, at timescales so brief they exist below the threshold of direct observation. If light were stopped, would these quantum fluctuations of space-time cease as well? Would the foam-like structure of space and time at quantum scales smooth out into perfect geometric regularity? Some theories in quantum gravity suggest that space-time itself might be made up of discrete units, tiny pixels of reality that combine to create the smooth space-time we observe at larger scales. These theories propose that time itself might flow in discrete steps rather than continuously, with each quantum tick of the cosmic clock corresponding to the time it takes light to cross one unit of space. If this picture is correct, then stopping light might indeed stop the fundamental ticking of time itself, freezing the quantum processes that create the flow of temporal experience. The relationship between light and space-time also extends to the very definition of simultaneity. In Einstein's relativity, there is no universal now that applies throughout the cosmos. Events that appear simultaneous to one observer may occur at different times for another observer moving at a different velocity. Light signals are what allow us to compare clocks and establish the timing of distant events. Without light to carry timing information, the very concept of simultaneity might lose its meaning, leaving each point in space isolated in its own temporal reference frame. This isolation might create a universe where time flows differently at every location, with no way to synchronize or compare temporal experiences across space. Each atom, each particle, each region of space-time might drift into its own temporal rhythm, creating a cosmos where the unified flow of time fractures into countless individual streams, each flowing at its own rate, each cut off from all others. Perhaps most profoundly, the connection between light and space-time suggests that stopping light might not just freeze time, but might fundamentally alter the dimensionality of reality itself. In our universe, space has 3 dimensions, and time has 1, creating the 4-dimensional space-time continuum. But this structure depends on the existence of light speed as the conversion factor between spatial and temporal measurements. Without light speed to connect space and time, might they separate back into independent entities? Would we find ourselves in a universe with 3 dimensions of space and no time at all? Or would time continue to flow in complete isolation from spatial dimensions? The implications extend to the very notion of distance and measurement. In relativity, the distance between 2 points in space-time depends not just on their spatial separation, but also on their separation in time. Light cones define the regions of space-time that can influence or be influenced by any given event. If light were stopped, these light cones would collapse, leaving each event completely isolated from all others. Space might lose its meaning as a connective medium, becoming instead a collection of isolated points with no relationship to each other. As we contemplate these possibilities, we begin to see that light is not merely fast-moving energy, but the very thread that weaves space and time into a coherent whole. Light creates the connections that allow cause and effect to operate across distance, enables the synchronization of clocks across space, and provides the geometric structure that makes space-time a unified entity rather than separate and unrelated dimensions. In stopping light, we might not just remove illumination from the universe, but might unravel the very fabric of space-time itself, creating a reality so alien to our experience that concepts like distance, causality, and even existence itself might lose all meaning. the universe might fragment into countless isolated points of being, each existing in perfect solitude, each unable to influence or be influenced by anything else. Time flows with the rhythm of light, as space bends and stretches around us. But what would happen if that rhythm were to stop? Would the cosmic dance freeze in place? Or would space-time itself come apart at the seams, leaving us in a reality where space and time exist in eternal isolation from each other? Light is perhaps the most mysterious phenomenon in our universe, existing in a state that defies our everyday understanding of reality. For centuries, scientists debated whether light was made of particles or waves, never imagining that the answer would be both and neither. This fundamental duality lies at the heart of quantum mechanics and reveals the strange nature of reality at its most basic level. When Isaac Newton studied light in the 1600s, he proposed that it consisted of tiny particles he called corpuscles. These light particles would travel in straight lines, bounce off mirrors, and carry energy from place to place. This particle theory explained many observations, such as why light casts sharp shadows and how it can exert pressure on objects. But other scientists, particularly Christian Huygens, argued that light behaved like waves rippling through an invisible medium they called the luminiferous ether. The wave theory gained strength in the early 1800s when Thomas Young performed his famous double-slit experiment. He shone light through two parallel slits cut in a barrier and observed the pattern it created on a screen behind. Instead of seeing two bright lines corresponding to the slits, Young saw a series of alternating bright and dark bands. This interference pattern could only be explained if light was behaving like waves, with peaks and troughs adding together or cancelling each other out. For over a century, the wave theory dominated scientific thinking about light. James Clerk Maxwell's equations in the 1860s showed that light was electromagnetic radiation, consisting of oscillating electric and magnetic fields that propagated through space at the cosmic speed limit. These electromagnetic waves could have different frequencies and wavelengths, explaining the entire spectrum of light from radio waves to gamma rays. Everything seemed to fall into place with the wave picture of light. But at the dawn of the 20th century, new observations began to challenge this comfortable understanding. When scientists studied how hot objects emit light, they discovered that the energy was not distributed smoothly across all wavelengths as wave theory predicted. Instead, energy seemed to come in discrete chunks or packets. Max Planck, in 1900, reluctantly proposed that light energy could only be emitted in specific amounts, which he called quanta. Einstein took this idea further in 1905, suggesting that light itself was made of particles he called photons. Each photon carried a specific amount of energy related to its frequency, with higher frequency light containing more energetic photons. This explained the photoelectric effect, where light hitting certain metals would knock electrons loose, but only if the light frequency was above a certain threshold. No matter how bright the light, if the frequency was too low, no electrons would be ejected. This could only make sense if light came in particle-like packets of energy. The discovery that light behaves as both wave and particle created one of the most profound puzzles in physics. How could something be both a continuous wave rippling through space and a discrete particle bouncing around like a tiny billiard ball? The answer revealed the quantum nature of reality itself, where objects exist in states that transcend our classical understanding of what it means to be a thing. In the quantum world, light exists in what physicists call a superposition of states. A single photon can travel through both slits in Young's experiments simultaneously, interfering with itself to create the wave pattern we observe. But the moment we try to detect which slit the photon passed through, the wave pattern disappears, and the photon behaves like a particle, going through one slit or the other, but never both. The very act of observation seems to collapse the wave function, forcing light to choose between its wave and particle nature. This strange behavior extends beyond light to all quantum objects. Electrons, protons, even entire atoms can display wave-particle duality under the right conditions. But photons are special because they have no mass and always travel at light speed. They cannot be slowed down or stopped in the conventional sense, existing only in motion at the cosmic speed limit. This gives photons a unique relationship with space and time that differs from all other particles. Photons also carry more than just energy, they carry information. Every photon that reaches your eye contains information about where it came from, what it interacted with along the way, and the conditions present when it was created. The light from distant stars carries information about the nuclear processes in their cores, the composition of their atmospheres, and the gravitational fields they move through. Radio waves from spacecraft carry digital data encoded in their electromagnetic oscillations. Even the light bouncing off this page carries information about the ink patterns that form these words. The relationship between photons and information becomes even more intriguing when we consider quantum entanglement. Two photons can become entangled, sharing a quantum connection that persists even when they are separated by vast distances. Measuring the properties of one entangled photon instantly determines the properties of its partner, regardless of how far apart they are. This quantum correlation seems to violate the principle that nothing can travel faster than light, yet it has been confirmed in countless experiments. Einstein famously called entanglement spooky action at a distance because he was uncomfortable with the idea that the universe could contain these instantaneous connections. But quantum mechanics insists that entangled particles share a single quantum state that cannot be described by considering the particles separately. The entanglement does not allow information to travel faster than light, but it does reveal that the quantum world contains correlations that transcend our classical understanding of locality and causality. If light were stopped, what would happen to these quantum correlations? Would entangled photons lose their connection? Or would the quantum state persist even in the absence of light propagation? The answer might depend on whether stopping light affects only the motion of photons or the underlying quantum fields from which photons emerge. Quantum field theory describes photons as excitations in the electromagnetic field that permeates all of space. If this field itself were frozen, the very foundation of electromagnetic phenomena might cease to exist. The quantum vacuum, the lowest energy state of space, is not truly empty, but seethes with virtual particles that pop in and out of existence. Virtual photons mediate the electromagnetic force between charged particles, creating the attractions and repulsions that hold atoms together and power chemical reactions. These virtual particles exist for such brief moments that they seem to violate conservation of energy, borrowing energy from the vacuum and paying it back before the universe notices the debt. If light were stopped, would these virtual photons cease to exist? Would the electromagnetic force itself disappear, causing atoms to fall apart as their electrons lose the electromagnetic attraction that keeps them bound to their nuclei? The implications extend to the very stability of matter itself. Without electromagnetic forces, the chemical bonds that hold molecules together might dissolve, reducing all complex structures to isolated atomic nuclei surrounded by unbound electron clouds. The dual nature of light also raises questions about the nature of time itself at the quantum level. Photons, having no rest mass, do not experience time in the way that massive particles do. From a photon's perspective, if it could have a perspective, its journey from creation to destruction happens instantaneously, regardless of how far it travels through space. The billions of years it takes light to travel from distant galaxies to our telescopes pass in zero time from the photon's reference frame. This timeless existence of photons creates a strange relationship between light and temporal flow. Light connects different moments in time, carrying information from the past to the present, but exists outside the normal flow of time itself. If light was stopped, would this temporal connection be severed? Would the universe fragment into isolated moments, each cut off from past and future by the absence of light to carry temporal information? The quantum measurement problem adds another layer to these mysteries. In quantum mechanics, particles exist in superposition states until they are measured or observed. The act of measurement collapses the wave function, forcing the particle to choose specific properties from among all the possibilities it contained. But what constitutes a measurement? Some interpretations suggest that consciousness plays a role, while others propose that any interaction with the environment is sufficient to collapse the wave function. Photons play a crucial role in most quantum measurements because they carry information from the quantum system to the measuring device. If light were stopped, would quantum systems remain forever in superposition, unable to collapse into definite states? Would the universe become a realm of pure potential, where nothing ever becomes actual because there is no way for measurements to occur? The relationship between light and information extends to the very structure of physical law. The electromagnetic field obeys Maxwell's equations, mathematical relationships that describe how electric and magnetic fields interact and propagate. These equations are time reversible, meaning that electromagnetic phenomena should be able to run backward in time just as easily as forward. Yet we never see light converging from all directions to create a bright flash that then disappears into a light bulb. This asymmetry points to the deep connection between light, information, and the arrow of time. Information generally flows from organized states to disorganized ones, from low entropy to high entropy. Light carries this information flow, spreading energy and information from concentrated sources to the vast emptiness of space. If light were stopped, would the arrow of time itself become confused? Would the universe lose its sense of direction, unsure whether to move toward past or future? The particle aspect of light also relates to the quantization of energy and action in the universe. Planck's constant, one of the fundamental constants of nature, determines the size of energy quanta and sets the scale at which quantum effects become important. This constant appears in the relationship between photon energy and frequency, linking the wave and particle aspects of light. If light behavior changed, it might indicate changes in the fundamental constants that govern reality. Some theories suggest that the constants of nature might have evolved over cosmic time, slowly changing as the universe aged and expanded. If light could be stopped, it might provide a window into understanding whether these constants are truly constant or whether they emerge from deeper principles that could be altered under extreme conditions. The ability to manipulate light might give us control over the fundamental parameters that determine how reality operates. The wave-like properties of light also connect to the concept of resonance, where systems naturally oscillate at specific frequencies. Atoms absorb and emit light at precise wavelengths determined by their electron energy levels. These atomic transitions are so regular they form the basis for our most accurate clocks and our definitions of fundamental units like the meter. If light were stopped, would atomic resonances cease? Would the natural frequencies that govern everything from molecular vibrations to planetary orbits fall silent? Light also exhibits properties like polarization, where the electric field oscillates in specific directions, perpendicular to the direction of travel. Polarized light reveals information about magnetic fields in space, the structure of materials it passes through, and the rotation of distant astronomical objects. This directional aspect of light adds another dimension to its information, carrying capacity and its role in revealing the hidden properties of the universe. As we explore the dual nature of light, we begin to see that photons are not simply fast-moving particles or oscillating waves. but something far more fundamental to the structure of reality itself. They are the quantum messengers that connect all parts of the universe, the carriers of electromagnetic force, the mediators of information transfer, and the foundation upon which our understanding of space and time is built. In contemplating what would happen if light was stopped, we are really asking about the fate of information, measurement, causality, and the very quantum processes that create the rich complexity of our universe. Would stopping light freeze these processes, or would we discover that reality has deeper layers that operate independently of electromagnetic phenomena? Light's particle-like properties allow it to carry information across the universe, but could it be possible to stop light, freezing the flow of information in the process? Or would the universe find other ways to maintain the connections that make existence possible? The relationship between light and our perception of time runs far deeper than most people realize. Every moment of conscious experience depends on light signals reaching our brains, creating the rich tapestry of sensory information that forms our awareness of the present moment. But what would happen to our perception of time if light itself could be stopped? Would consciousness freeze along with the photons, or would we continue to experience the flow of time in ways we cannot currently imagine? Human perception of time is intricately woven with visual experience. When you watch a clock tick, see leaves falling from a tree, or observe the movement of clouds across the sky, you are witnessing change through the arrival of light signals at your eyes. These photons carry information about the positions and properties of objects at the moment they were emitted or reflected. Your brain processes this continuous stream of visual information to construct your sense of the present moment and your awareness of temporal flow. But vision is not the only sense that depends on electromagnetic phenomena. The electrical signals that carry information through your nervous system are fundamentally electromagnetic in nature. Every time a neuron fires, it creates an electrical impulse that travels along nerve fibers to communicate with other cells. These neural signals depend on the movement of charged particles, primarily sodium and potassium ions, across cell membranes. The electromagnetic forces that govern these ionic movements are mediated by virtual photons, the same quantum messengers that carry the electromagnetic force throughout the universe. If light were truly stopped, including the virtual photons that mediate electromagnetic interactions, the electrical activity in your brain might cease entirely. Neural networks that normally buzz with electrochemical activity could fall silent, frozen in whatever state they occupied at the moment of light cessation. Memory formation, which depends on electrical changes in neural connections, might become impossible. Consciousness itself, arising from complex patterns of electrical activity across billions of neurons, could vanish in an instant. Yet this scenario assumes that stopping light would affect all electromagnetic phenomena. Perhaps there are forms of electromagnetic activity that could persist even if photons traveling through space were halted. The electrical fields within individual atoms might continue to operate, allowing neural activity to persist even in a universe where light could no longer propagate between distant points. In this case, consciousness might continue, but our perception of time would be radically altered. Consider what your experience of time would become without any visual input. In darkness, humans rely more heavily on other senses to gauge the passage of time. The rhythmic beating of your heart, the cycle of breathing, the gradual accumulation of fatigue, and the slow processes of hunger and thirst all provide internal clocks that tick independently of light. These biological rhythms are governed by complex molecular processes that might continue even if electromagnetic radiation could no longer travel through space. Your circadian rhythm, the internal biological clock that regulates sleep and wakefulness, is normally synchronized by exposure to daylight. But this 24-hour cycle can persist for weeks or months, even in complete darkness, suggesting that it depends on internal molecular clocks rather than direct light input. These cellular timekeepers are based on the production and breakdown of specific proteins in a feedback loop that takes approximately 1 day to complete. If light was stopped, but molecular processes continued, your internal sense of day and night might persist even in eternal darkness. The perception of shorter time intervals would become much more challenging without visual cues. Studies of people in sensory deprivation chambers show that time estimation becomes highly unreliable when visual and auditory input is removed. Minutes can feel like hours, or hours can seem to pass in what feels like minutes. Without the constant stream of visual information that normally anchors our perception to external events, the subjective experience of time becomes fluid and unpredictable. But perhaps the most profound impact on time perception would come from the loss of causality that stopping light might create. Our understanding of cause and effect depends heavily on observing sequences of events through vision. We see one thing happen, then observe its consequences, and our brains construct narratives of temporal flow based on these observed sequences. Without light to carry information about distant events, each person would become isolated in their immediate vicinity, aware only of changes occurring within reach of their other senses. This isolation might fragment the shared experience of time that normally synchronizes human activity. Currently, we use light signals, whether from the sun, clocks, or electronic devices, to coordinate our activities across space. Millions of people can simultaneously experience the same moment by observing the same light signals. If light were stopped, this temporal coordination would become impossible. Each person would drift into their own private experience of time, with no way to verify that their temporal experience matched that of others. The psychological impact of such isolation could be profound. Humans are social creatures whose sense of reality is constantly validated by shared experiences with others. Our perception of time is partly constructed through social interaction, through conversations about past events and plans for the future. Without light to enable visual communication, and with only sound waves traveling at their much slower pace, social coordination would become extremely limited. Each person might develop their own unique relationship with time, their own private temporal reality. Memory would play an increasingly important role in time perception if light was stopped. Without new visual experiences to mark the passage of time, consciousness might turn inward, relying more heavily on the recall of past events to maintain a sense of temporal continuity. But memory itself is reconstructive, constantly changing each time we recall an event. In a world without light, the boundaries between memory and present experience might blur, creating a dreamlike state where past and present become increasingly difficult to distinguish. The absence of light might also affect the neurochemical basis of time perception. The production of neurotransmitters like serotonin and dopamine, which influence mood and the subjective experience of time, is partly regulated by light exposure. Seasonal affective disorder demonstrates how reduced light can alter brain chemistry and affect time perception. In permanent darkness, these neurochemical changes might create altered states of consciousness where time feels dramatically different from normal waking experience. Some research suggests that the brain contains multiple internal clocks operating at different timescales. There are millisecond timers that coordinate motor movements, second-to-minute timers that track ongoing events, and circadian rhythms that operate over daily cycles. Different brain regions seem to be responsible for different aspects of temporal processing. If light was stopped, some of these timing systems might continue while others fail, creating a fragmented experience of time where different aspects of temporal awareness operate independently. The phenomenon of time dilation in extreme psychological states provides clues about how time perception might change in a lightless universe. During life-threatening emergencies, many people report that time seems to slow down dramatically, allowing them to observe events in slow motion and react with unusual precision. This suggests that time perception is highly plastic and can be altered by changes in neural activity. In a world without light, similar alterations in consciousness might create entirely new forms of temporal experience. Dreams offer another window into how time perception might function without normal sensory input. During dreams, time often behaves strangely, with events that seem to last hours fitting into minutes of real time, or brief dream moments feeling like they extend for days. The dreaming brain creates rich temporal narratives without relying on external light signals, suggesting that consciousness has an innate capacity to generate time perception independently of electromagnetic input. The role of attention in time perception becomes crucial in considering a lightless universe. Normally, our attention is constantly drawn to visual stimuli, creating a stream of conscious moments that feel connected in time. Without visual input, attention would need to focus entirely on internal mental processes, bodily sensations, and the limited information available through other senses. This dramatic shift in attentional focus might create forms of consciousness similar to deep meditative states, where time perception can become radically altered. Some meditation practitioners report experiences where time seems to stop entirely, where consciousness exists in an eternal present moment without past or future. If light was stopped and normal sensory experience ceased, human consciousness might naturally drift into such states. The ordinary experience of time as a flowing river might be replaced by awareness of time as a vast ocean, present all at once, rather than experienced sequentially. The absence of light might also reveal aspects of time perception that are normally hidden by the constant bombardment of visual information. Some people with congenital blindness report having a different relationship with time, relying more heavily on memory, rhythm, and internal bodily cues to navigate temporal experience. Their insights suggest that human time perception is more flexible and adaptable than those of us who rely heavily on vision might assume. If stopping light affected only photons traveling through space but left local electromagnetic phenomena intact, time perception might change in more subtle ways. The loss of information from distant events would create a kind of temporal horizon beyond which nothing could be known. Each person would exist in a bubble of present moment awareness, cut off from the broader temporal context that normally connects individual experience to the larger flow of cosmic time. The philosophical implications become staggering when we consider that time perception might be the foundation of all conscious experience. If consciousness is the universe becoming aware of itself, then time perception is how that awareness unfolds moment by moment. Stopping light might not just change how we perceive time, it might alter the very nature of consciousness itself, creating forms of awareness that transcend our current understanding of what it means to exist in time. The quantum nature of consciousness, if it exists, might also be affected by stopping light. Some theories suggest that consciousness arises from quantum processes in the brain, involving quantum entanglement between neurons or quantum computations in cellular structures called microtubules. If light was stopped and quantum entanglement affected, these hypothetical quantum aspects of consciousness might be disrupted, potentially altering not just time perception, but the very structure of conscious experience. Yet perhaps consciousness would adapt to a lightless universe in ways we cannot anticipate. Human awareness has proven remarkably flexible throughout history, adapting to new technologies, environments, and ways of living. The brain's plasticity might allow it to develop new forms of time perception based on whatever sensory and cognitive resources remain available. Consciousness might discover forms of temporal awareness that are currently hidden by our dependence on light-based perception? Could the very act of stopping light alter our perception of time? Or would time continue its unrelenting march, unaffected by the absence of light, leaving consciousness to discover new ways of dancing with temporal flow in a universe where the music of electromagnetic radiation has fallen silent? The answer might reveal whether time perception is merely a byproduct of light-based information processing, or whether it represents something deeper about the nature of consciousness and its relationship to the fundamental structure of reality. As objects approach the speed of light, something extraordinary happens to the flow of time itself. This phenomenon, called time dilation, represents one of the most profound and counterintuitive discoveries in the history of science. Understanding how time behaves at extreme velocities provides crucial insights into what might happen if light itself could be stopped, frozen in place throughout the universe. Time dilation emerges from the fundamental structure of space-time itself. According to Einstein's special theory of relativity, time is not the universal constant we once believed it to be. Instead, time flows differently for observers moving at different velocities relative to each other. The faster you move through space, the slower you move through time. This is not merely a theoretical curiosity, but a measurable effect that becomes increasingly dramatic as velocities approach light speed. Imagine a spacecraft accelerating away from Earth at ever-increasing speeds. At low velocities, the time dilation effect is negligible. A spacecraft traveling at 1,000 kilometers per hour would experience time flowing only slightly differently than clocks on Earth, with the difference measured in nanoseconds over years of travel. But as the spacecraft approaches significant fractions of light speed, the effects become dramatic and impossible to ignore. At 50% of light speed, time aboard the spacecraft would flow at about 87% the rate of Earth time. A journey that takes 10 years from Earth's perspective would feel like only 8 years and 8 months to the travelers. This difference, while significant, is still relatively modest compared to what happens at even higher velocities. When the spacecraft reaches 90% of light speed, time dilation becomes extreme. Time aboard the ship flows at only about 44% the rate of Earth time. A 10-year journey from Earth's perspective would feel like less than 4.5 years to the travelers. The spacecraft would be racing not just through space but through time itself, moving toward the future at an accelerated rate compared to the rest of the universe. At 99% of light speed, the effects become almost unimaginable. Time aboard the spacecraft slows to just 14% of Earth's rate. That same 10-year journey would feel like only 1 year and 5 months to the travelers. They would age more than 7 times slower than people on Earth, effectively traveling into the future while remaining young. But the most extreme case occurs at 99.9% of light speed. Here, time dilation reaches factors of over 22 to 1. Time aboard the spacecraft flows at less than 5% of Earth's rate. A journey that appears to take 10 years from Earth would feel like less than 5 months to the travelers. They would experience the universe rushing past them in fast forward while they moved through time at a crawl. As velocity approaches exactly 100% of light speed, something theoretically remarkable happens. The time dilation factor approaches infinity, meaning that time aboard the spacecraft would approach a complete stop relative to outside observers. At exactly light speed, if it were possible for massive objects to reach it, time would cease to flow entirely from the perspective of external observers. This mathematical relationship suggests a profound connection between light speed and the nature of time itself. Light speed is not just the fastest possible velocity, it represents the speed at which time stops flowing. Photons, which always travel at light speed, experience no passage of time during their journeys. From a photon's perspective, its entire existence from creation to absorption happens in a single instant, regardless of whether it travels across a room or across the universe. The implications become even more intriguing when we consider what happens to objects already traveling at light speed if the cosmic speed limit itself could be altered. Photons exist in a state where time has already stopped from their own reference frame. If light were brought to a complete halt, what would happen to this temporal relationship? Would photons suddenly begin to experience time, or would they enter an even more exotic state beyond our current understanding? Real-world evidence for time dilation comes from numerous experimental confirmations. Atomic clocks flown on high-speed aircraft show measurable time differences compared to identical clocks left on the ground. Particles created in cosmic ray collisions high in Earth's atmosphere live much longer than they should, based on their known decay rates, surviving their journey to Earth's surface, only because time dilation extends their lifespans from their own perspective. GPS satellites provide a daily demonstration of time dilation effects. These satellites orbit Earth at speeds of about 14,000 kilometers per hour and experience slightly less gravitational pull than objects on Earth's surface. Both effects cause time to flow differently aboard the satellites compared to Earth. Without constant corrections for these relativistic effects, GPS positioning would become inaccurate by several kilometers within just a few hours. The twin paradox illustrates the dramatic personal consequences of time dilation. If one twin travels to a distant star at near light speed while the other remains on Earth, the traveling twin will age much more slowly during the journey. Upon returning to Earth, the traveling twin might have aged only a few years, while the Earth-bound twin has aged decades. This is not science fiction, but a mathematical consequence of the structure of space-time itself. Time dilation reveals that simultaneity is relative. Events that appear simultaneous to one observer may occur at different times for another observer moving at a different velocity. This challenges our intuitive notion of universal time and suggests that the concept of now throughout the universe is meaningless. Each observer carries their own version of the present moment, synchronized only with events in their immediate vicinity. The energy required to accelerate massive objects to near light speeds becomes infinite as velocity approaches light speed. This energy barrier prevents any object with mass from actually reaching light speed, preserving the special status of photons as the only entities that naturally exist at this cosmic speed limit. But it also suggests that light speed represents more than just a velocity. It represents a fundamental boundary in the structure of reality itself. If we could somehow stop light throughout the universe, we would be altering this fundamental boundary condition. The mathematical relationships that govern time dilation are based on the assumption that light speed is constant and represents the maximum possible velocity. Changing this parameter might not just stop photons, but could fundamentally alter the flow of time for all objects in the universe. Consider what would happen to the time dilation experienced by fast-moving objects if light speed were reduced to zero. Currently, time dilation depends on the ratio between an object's velocity and light speed. If light speed became zero, this ratio would become infinite for any moving object, suggesting that time might stop flowing for anything in motion. The universe might freeze into a state where only perfectly stationary objects could continue to experience time. Alternatively, reducing light speed to zero might eliminate time dilation entirely, allowing time to flow at the same rate for all observers regardless of their motion. This would restore the absolute time that existed in Newtonian physics, where simultaneity was universal and time flowed at the same rate throughout the cosmos. Such a change would fundamentally alter the structure of space-time and might have consequences we cannot currently imagine. The relationship between time dilation and gravitational effects adds another layer to this puzzle. General relativity shows that gravity also dilates time, with stronger gravitational fields causing time to flow more slowly. This gravitational time dilation is related to the curvature of space-time caused by mass and energy. If stopping light affected the propagation of gravitational effects, it might also alter gravitational time dilation throughout the universe. Time dilation effects become extreme near the event horizons of black holes, where gravitational fields approach infinite strength. An outside observer would see time slow to a stop for anything falling into a black hole, while the falling observer would experience time normally until reaching the singularity. If light were stopped throughout the universe, would these extreme gravitational time dilation effects persist? Or would they disappear along with the electromagnetic phenomena that normally allow us to observe them? The quantum mechanical aspects of time dilation introduce additional complexities. Quantum field theory describes particles as excitations in underlying fields that exist throughout space. Time dilation affects these quantum fields, altering the rates at which quantum processes occur. Virtual particles that mediate fundamental forces might experience altered lifetimes in reference frames with different time flow rates. Stopping light might disrupt these quantum processes in ways that cascade through all of physics. Particle accelerators routinely create conditions where time dilation becomes significant. Subatomic particles accelerated to near light speeds experience dramatically extended lifetimes, allowing scientists to study unstable particles that would otherwise decay too quickly to observe. These experiments confirm that time dilation affects all forms of matter and energy, suggesting that stopping light might have universal consequences for temporal flow. The philosophical implications of time dilation challenge our deepest assumptions about the nature of existence. If time can flow at different rates for different observers, what does it mean to say that events happen now, or that time has a direction? Time dilation reveals that time is not a universal backdrop against which events unfold, but is instead intimately connected to matter, energy, and motion through the fabric of space-time. Some interpretations of quantum mechanics suggest that consciousness plays a role in collapsing quantum wave functions and determining the flow of time. If this is true, then time dilation might affect not just physical processes, but the very nature of conscious experience. Travelers at near light speeds might not only age more slowly, but might experience consciousness itself flowing at a different rate. The possibility of closed time-like curves, theoretical paths through space-time that loop back to earlier times, becomes relevant when considering extreme time dilation scenarios. While such curves are generally thought to be prohibited by the laws of physics, they illustrate how dramatic alterations to the flow of time might create paradoxical situations where cause and effect become scrambled. Time dilation also affects the decay rates of radioactive materials, the frequencies of atomic transitions, and the rates of all physical and chemical processes. A universe where light had been stopped might see these fundamental rates frozen or altered in ways that change the very nature of matter and energy. The periodic table of elements might behave differently. Stars might cease their nuclear fusion, and the complex chemistry that enables life might grind to a halt. Yet perhaps the most profound question raised by time dilation is whether time itself is fundamental or emergent. If time can be dilated, stretched, and potentially stopped, is it a basic feature of reality or a consequence of deeper principles? The ability to stop light might provide a window into understanding whether time is woven into the fabric of existence, or whether it emerges from more fundamental processes that could continue even in a lightless universe. The mathematics of time dilation suggest that reaching light speed would cause time to stop entirely for the traveler, while the rest of the universe rushed past in fast forward. But what would happen if the entire universe reached this condition simultaneously? If light everywhere were stopped, would time stop flowing for everything, creating a frozen cosmos where change becomes impossible? Or would we discover that time has depths we have not yet explored, layers of temporal flow that operate independently of electromagnetic phenomena? At the edge of light speed, time bends in strange ways, but could stopping light entirely have even more profound effects on the flow of time, revealing aspects of temporal reality that remain hidden as long as photons race through the cosmos at their cosmic speed limit. Black holes represent the ultimate laboratory for understanding the relationship between light and time. These cosmic monsters create regions of spacetime so severely warped that not even light can escape their gravitational embrace. At the event horizon, the boundary of no return, light reaches its absolute limit, unable to propagate outward despite traveling at the cosmic speed limit. Understanding what happens to time at this extreme boundary provides profound insights into what might occur if light could be stopped throughout the entire universe. The event horizon is perhaps the most mysterious boundary in all of physics. It marks the point where the escape velocity required to leave the black hole equals the speed of light. Inside this boundary, space-time is so severely curved that all paths lead inexorably toward the central singularity. Even light, following the straightest possible path through curved space-time, cannot escape once it crosses this threshold. The event horizon creates a one-way membrane that allows matter and energy to fall in, but prevents anything from coming back out. From the perspective of an outside observer, something remarkable happens to time near the event horizon. As an object falls toward a black hole, gravitational time dilation causes its clocks to appear to slow down relative to distant observers. The closer the object gets to the event horizon, the more dramatically time appears to slow. At the event horizon itself, time dilation becomes infinite from the outside perspective. Clocks would appear to stop ticking entirely, freezing the falling object at the boundary for all eternity. This creates one of the most profound paradoxes in physics. An outside observer would never actually see anything cross the event horizon. Instead, they would watch objects slow down and fade away as they approach the boundary, their light becoming increasingly red-shifted until it disappears into infrared wavelengths and beyond. The object would appear frozen at the event horizon, its image preserved forever at the moment of crossing. Yet from the perspective of the falling observer, nothing special happens at the event horizon. They continue falling normally, crossing the boundary in finite time according to their own clocks. This paradox reveals the relative nature of time and the crucial role that light plays in connecting different regions of space-time. The outside observer relies on light signals from the falling object to determine what is happening. As gravitational time dilation becomes extreme, these light signals become increasingly stretched out in time, creating the illusion that time has stopped. But this is only an illusion created by light's inability to escape the gravitational field. Inside the event horizon, time continues to flow normally for the falling observer. But the structure of space-time itself has changed in fundamental ways. The roles of space and time become interchanged. Outside the black hole, moving through space is optional, while moving through time is inevitable. Inside the event horizon, moving toward the singularity becomes as inevitable as the forward flow of time was outside. The falling observer cannot stop their motion toward the center any more than they could stop aging before crossing the horizon. The singularity at the center of a black hole represents the ultimate breakdown of our understanding of space-time. Here, gravitational fields become infinite, matter is compressed to infinite density, and the curvature of space-time reaches impossible extremes. Time itself may cease to have meaning at the singularity, where the normal rules of physics break down entirely. Some theories suggest that time might flow backward near the singularity, or that multiple timelines might converge into a single point. If light was stopped throughout the universe, would the event horizons of black holes lose their meaning? The boundary is defined by the condition that light cannot escape. But if light were not moving anywhere in the universe, this definition would need to be reconsidered. Perhaps event horizons would expand to encompass regions where other forms of information or causality could not escape. Or perhaps they would disappear entirely if the fundamental structure of space-time were altered. The Hawking radiation emitted by black holes provides another perspective on the relationship between light and time near event horizons. According to quantum field theory, the intense gravitational fields near black holes create particle-antiparticle pairs from the quantum vacuum. When these pairs form near the event horizon, one particle may fall into the black hole while the other escapes as radiation. This process allows black holes to slowly evaporate over cosmic timescales, with smaller black holes radiating away their mass faster than larger ones. The temperature of Hawking radiation is inversely related to the black hole's mass. Stellar mass black holes have temperatures just billionths of a degree above absolute zero, meaning they radiate extremely slowly. But as black holes lose mass through evaporation, their temperature increases and the radiation process accelerates. In the final moments of a black hole's life, it would explode in a burst of high-energy radiation as the last of its mass converts to energy. If light were stopped, would Hawking radiation cease to exist? This quantum process depends on the creation and separation of particle pairs near the event horizon, with photons carrying energy away from the black hole. Without the ability for light to propagate, black holes might become truly permanent fixtures in the universe, unable to evaporate and return their captured mass and energy to the cosmos. The information paradox associated with black holes becomes even more puzzling when considering a universe where light has been stopped. According to quantum mechanics, information cannot be destroyed, yet black holes seem to erase all information about the matter that falls into them. When black holes evaporate through Hawking radiation, the radiation appears to be thermal and random, carrying no information about what fell in. This creates a paradox between quantum mechanics and general relativity. Various solutions to the information paradox have been proposed, including the idea that information is encoded in the Hawking radiation in subtle ways that preserve quantum correlations. Other theories suggest that information is stored at the event horizon, or that black holes never fully evaporate, but leave behind remnants containing all the information they absorbed. If light was stopped, these information preservation mechanisms might be disrupted, potentially resolving the paradox in unexpected ways, or creating new paradoxes we cannot currently imagine. The complementarity principle in black hole physics suggests that the same physical process can be described differently depending on the observer's frame of reference. An outside observer sees matter hitting the event horizon and being incorporated into the black hole's mass. But from the perspective of someone falling in, they pass through empty space and continue toward the singularity. Both descriptions are equally valid, demonstrating the relative nature of physical reality near black holes. This complementarity depends on the different ways that light signals propagate in the curved spacetime around black holes. If light could not propagate at all, would complementarity break down? Would there be a single, universal description of what happens near black holes? Or would the absence of light create even stranger forms of observer-dependent reality? Wormholes, hypothetical shortcuts through space-time that connect distant regions of the universe, are often associated with black holes in popular imagination. Some theoretical wormholes might have event horizons that prevent two-way travel, while others might allow passage in both directions. The stability of wormholes depends on exotic matter with negative energy density, creating gravitational effects that oppose the normal tendency of spacetime to curve inward. If light were stopped, the propagation of information through wormholes would be impossible, effectively cutting off these potential connections between distant parts of the universe. Even if wormholes existed, they would become useless as shortcuts if no information could travel through them. The universe might fragment into isolated regions connected by unusable spacetime tunnels. The ergosphere around rotating black holes, called Kerr black holes, creates another exotic region where the structure of space-time becomes severely distorted. In the ergosphere, space-time itself is dragged around by the rotating black hole, forcing everything within this region to rotate along with it. Light emitted in the ergosphere cannot remain stationary relative to distant observers, but must participate in the rotation of space-time itself. The Penrose process allows energy to be extracted from rotating black holes by dropping objects into the ergosphere in carefully designed trajectories. This process can theoretically extract up to 42% of a black hole's rest mass energy, making rotating black holes potential sources of enormous power for advanced civilizations. If light were stopped, would the ergosphere still drag space-time around the black hole? Or would this frame-dragging effect disappear along with the propagation of electromagnetic fields? White holes, the theoretical time-reversed versions of black holes, would expel matter and energy rather than absorbing them. While no white holes have been observed in nature, they represent valid solutions to Einstein's equations and might have existed in the early universe. A white hole would have an event horizon that prevents anything from falling in, while allowing unlimited outflow of matter and energy. The relationship between black holes and white holes involves a reversal of time's arrow. If black holes represent the ultimate future for matter falling into them, white holes would represent the ultimate past, spewing forth matter that appeared to come from nowhere. If light were stopped, would this temporal relationship between black and white holes be severed? Would time's arrow lose its meaning in regions where light could not carry information about causality? Primordial black holes, formed in the early universe from density fluctuations rather than stellar collapse, might have masses ranging from microscopic to stellar scales. These ancient black holes would have been evaporating through Hawking radiation for billions of years, with the smallest ones potentially exploding in the present era. The gamma-ray bursts from evaporating primordial black holes might be detectable by current instruments, providing evidence for both Hawking radiation and the existence of these exotic objects. If light were stopped, primordial black holes that were on the verge of evaporating might become frozen in time, unable to complete their final explosive moments. The universe might be populated with countless tiny black holes, suspended permanently at the moment before their final burst, creating a cosmic museum of quantum gravitational effects preserved for eternity. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary surface. For black holes, this means that everything that falls past the event horizon might be recorded as information on the horizon's surface. This principle has profound implications for the nature of space, time, and information, suggesting that three-dimensional reality might be an illusion projected from two-dimensional information. If light were stopped, would the holographic encoding of information on event horizons cease to function? The principle depends on the ability of information to be processed and stored in ways that might require the propagation of electromagnetic fields. Without light to carry information, the boundary of a black hole might lose its ability to store holographic data about the interior. The final fate of black holes in an expanding universe depends on the balance between matter accretion and Hawking evaporation. In the far future, as stars burn out and matter becomes increasingly dilute, black holes will begin to dominate the energy content of the universe. Eventually, they too will evaporate, leaving behind a cold, empty cosmos populated only by elementary particles and photons. But if light were stopped, this distant future might never arrive. Black holes would become permanent residents of the universe, unable to evaporate and return their mass to the cosmic inventory. The universe might evolve into a state dominated by these frozen gravitational archives, each one preserving a record of the matter and energy it captured during the era when light could still flow freely through space. The study of black holes has revealed that the relationship between gravity, light, and time is far more complex and beautiful than anyone imagined. These cosmic laboratories push the laws of physics to their limits, creating conditions where space and time exchange roles, where information might be preserved in ways that transcend our normal understanding, and where the very concepts of inside and outside lose their meaning. As we contemplate what would happen if light could be stopped throughout the universe, black holes provide crucial insights into how gravity and time might behave independently of electromagnetic phenomena. They suggest that space-time has a life of its own, capable of supporting exotic structures and phenomena even in the absence of light. Yet they also demonstrate how intimately connected light, gravity, and time really are, with each phenomenon depending on the others in ways that might make their complete separation impossible. Black holes challenge everything we know about light and time. Could the point at which light can no longer escape also be the point where time stops? Or would we discover that time has hidden depths that allow it to flow even in regions where light itself becomes trapped? The answer might determine whether stopping light would create cosmic prisons for time itself, or whether it would reveal new forms of temporal flow that operate beyond the reach of electromagnetic phenomena. At the quantum level, the relationship between light and time becomes even more mysterious and profound. In the realm of atoms and subatomic particles, light is not simply electromagnetic radiation traveling through space, but the fundamental mediator of one of nature's basic forces. Every interaction between charged particles, every chemical bond, every biological process depends on the exchange of virtual photons that exist for impossibly brief moments before disappearing back into the quantum vacuum. Understanding how light operates at this microscopic scale reveals whether time could continue to exist in a universe where photons had been stopped. Quantum mechanics describes a reality that seems to defy common sense, where particles exist in multiple states simultaneously until observed, where empty space seethes with virtual particles, and where the act of measurement fundamentally alters what is being measured. In this quantum realm, light plays multiple roles that extend far beyond its familiar properties as electromagnetic radiation. Photons are the quanta of the electromagnetic field, the discrete packets of energy that emerge when this field is excited above its ground state. The quantum vacuum, the lowest energy state of empty space, is not truly empty, but filled with fluctuations that create virtual particle pairs. These quantum fluctuations include virtual photons that pop in and out of existence at timescales, measured in units of Planck time, approximately 10 to the minus 43 seconds. These virtual photons are responsible for mediating the electromagnetic force between charged particles, creating the attractions and repulsions that hold atoms together and enable the complex chemistry of life. If light were stopped throughout the universe, what would happen to these virtual photons? Would the electromagnetic force itself disappear, causing atoms to fall apart as electrons lose their electromagnetic attraction to atomic nuclei? The answer depends on whether stopping light affects only real photons traveling through space, or whether it also eliminates the virtual photons that mediate electromagnetic interactions at the quantum level. Real photons, the kind we can detect with our instruments, are excitations of the electromagnetic field that propagate through space carrying energy and momentum. Virtual photons, by contrast, are fluctuations in the field that exist below the threshold of direct detection, but have measurable effects on the behavior of charged particles. The distinction between real and virtual photons is not absolute, but depends on the reference frame and the measurement process being used to observe them. Quantum field theory describes all particles as excitations in underlying fields that permeate space. The electromagnetic field exists everywhere, even in regions we consider empty, and photons are simply ripples in this field that carry energy from one location to another. If light were stopped, we might be freezing these ripples while leaving the underlying field intact, or we might be eliminating the field entirely, with consequences that cascade through all of physics. The uncertainty principle, one of the foundations of quantum mechanics, relates the precision with which we can know a particle's position and momentum. This principle also applies to energy and time, stating that we cannot know both the exact energy of a system and the exact time at which it has that energy. Virtual particles exploit this uncertainty, borrowing energy from the vacuum for brief periods before returning it, creating a constant dance of creation and annihilation that underlies all electromagnetic phenomena. Time plays a crucial role in quantum mechanics through the concept of wave function evolution. The Schrödinger equation describes how quantum systems change over time, with wave functions spreading and interfering as they evolve. This temporal evolution is what allows quantum systems to exist in superposition states and to exhibit the interference patterns that demonstrate wave-particle duality. If time were somehow altered by stopping light, would quantum evolution cease, freezing all quantum systems in their current states? The measurement problem in quantum mechanics becomes even more intriguing when considering a universe without light. Most quantum measurements involve the interaction of photons with quantum systems, allowing information about the system's state to be transferred to measuring devices. Without light to carry this information, how would quantum measurements occur? Would quantum systems remain forever in superposition, unable to collapse into definite states because no measurement could extract information about them? Quantum entanglement, the phenomenon Einstein called spooky action at a distance, creates correlations between particles that persist regardless of the distance separating them. When two particles become entangled, measuring one particle instantly determines the state of its partner, even if they are separated by vast distances. This correlation seems to violate the principle that information cannot travel faster than light, yet it has been confirmed in countless experiments. The role of light in quantum entanglement is complex and subtle. While the correlations between entangled particles appear instantaneous, no information can actually be transmitted faster than light through entanglement alone. The phenomenon does not violate causality because the correlations cannot be used to send messages or influence distant events. If light were stopped, would entangled particles maintain their correlations, or would these quantum connections be severed along with all other forms of information transfer? Quantum chromodynamics, the theory describing the strong nuclear force, involves the exchange of particles called gluons between quarks inside protons and neutrons. Unlike photons, which have no charge and do not interact with each other directly, gluons carry color charge and can interact with other gluons, creating a complex web of forces that confines quarks within nuclear particles. The strong force operates independently of electromagnetism and might continue to function even if light was stopped. The weak nuclear force, responsible for certain types of radioactive decay, is mediated by particles called W and Z bosons. These particles are much more massive than photons and have limited range, operating only over distances comparable to the size of atomic nuclei. Like the strong force, the weak force might continue to operate in a universe where electromagnetic radiation had been stopped, allowing certain forms of nuclear processes to continue. Atomic structure depends fundamentally on the electromagnetic force mediated by virtual photons. Electrons occupy specific energy levels around atomic nuclei, and they can only change levels by absorbing or emitting real photons with exactly the right energy. These atomic transitions are so precise, they form the basis for our most accurate clocks and our definitions of fundamental units like the meter and the second. If light were stopped, would atomic transitions cease to occur? Electrons might become frozen in their current energy levels, unable to absorb or emit the photons needed to change states. This could halt all chemistry, since chemical reactions depend on electrons moving between different energy configurations as atoms form and break bonds. The complex molecular machinery of life, from DNA replication to protein synthesis, might grind to a complete halt. Yet quantum tunneling, a purely quantum mechanical effect, allows particles to pass through energy barriers that would be impossible to cross according to classical physics. This process does not depend directly on electromagnetic radiation, but on the wave-like properties of matter itself. Quantum tunneling is responsible for radioactive decay, nuclear fusion in stars, and the operation of many electronic devices. If light was stopped but quantum mechanics continued to operate, tunneling might persist as one of the few remaining processes that could drive change in the universe. The vacuum decay phenomenon, a theoretical process where the lowest energy state of quantum fields might not be the true ground state, could have dramatic consequences if light were stopped. If the electromagnetic field exists in a false vacuum state, it might spontaneously decay to a lower energy configuration, releasing enormous amounts of energy and fundamentally altering the laws of physics. Stopping light might trigger such a decay or prevent it from occurring, depending on how the process affects the stability of quantum field configurations. Quantum computers rely on the manipulation of quantum states to perform calculations that would be impossible with classical computers. These devices use various physical systems, including trapped ions, superconducting circuits, and photonic systems that directly manipulate light quanta. If light were stopped, photonic quantum computers would cease to function, but other quantum computing approaches might continue to operate, suggesting that quantum information processing could persist even without electromagnetic radiation. The concept of quantum time, distinct from classical time, emerges from the fundamental role that measurement plays in quantum mechanics. Each quantum measurement can be thought of as a tick of a quantum clock, with the universe evolving from one measurement to the next in discrete steps rather than continuously. This quantum time might be more fundamental than the smooth time of classical physics, and could continue to flow even if classical electromagnetic phenomena were halted. Zero-point energy, the energy that quantum systems possess even at absolute zero temperature, represents the minimum energy required by the uncertainty principle. Even if all classical motion were stopped, quantum systems would retain this zero-point energy, creating fluctuations in motion that could never be eliminated. This suggests that some form of temporal evolution might persist at the quantum level, even in a universe where classical light propagation had ceased. The many worlds interpretation of quantum mechanics suggests that every quantum measurement causes the universe to split into multiple parallel realities, each corresponding to a different measurement outcome. In this view, time becomes the dimension along which these parallel universes branch and diverge. If light were stopped, would this branching process continue, creating new parallel worlds even in the absence of electromagnetic phenomena? Quantum field theory describes vacuum fluctuations as the constant creation and annihilation of virtual particle pairs, including virtual photon pairs. These fluctuations give the vacuum energy and contribute to measurable effects like the Casimir force between closely spaced conducting plates. If light were stopped, would these vacuum fluctuations cease, causing the energy density of space itself to change? Such a change might alter the expansion rate of the universe, or affect the stability of matter at the most fundamental level. The arrow of time, the fact that time flows forward rather than backward, might be connected to the quantum measurement process and the collapse of wave functions. Some interpretations suggest that consciousness plays a role in determining which quantum outcomes become real, linking the direction of time to the evolution of information and awareness. If light were stopped and quantum measurements could no longer occur, would the arrow of time lose its direction, allowing the universe to flow backward as easily as forward? Spontaneous symmetry breaking, the process by which symmetric quantum states evolve into asymmetric configurations, is responsible for giving mass to fundamental particles through the Higgs mechanism. This process involves the interaction of matter fields with the Higgs field, creating the particle masses we observe. If light were stopped, would spontaneous symmetry breaking continue to operate? Or would the masses of particles change as electromagnetic interactions cease to occur? The holographic principle in quantum gravity suggests that all information contained within a volume of space can be encoded on its boundary surface. This principle implies a deep connection between quantum information and the geometry of space-time itself. If light was stopped and information could no longer propagate, would the holographic structure of space collapse, causing three-dimensional reality to reduce to its two-dimensional boundary encoding? Quantum decoherence, the process by which quantum systems lose their coherence through interaction with their environment, is what allows classical behavior to emerge from quantum foundations. This process depends on the rapid exchange of information between quantum systems and their surroundings, typically mediated by photons and other particles. If light were stopped, would decoherence cease, causing the classical world to dissolve back into quantum superposition? The relationship between quantum mechanics and general relativity remains one of the greatest unsolved problems in physics. Quantum field theory describes matter and energy in terms of quantum fields, while general relativity describes gravity as the curvature of space-time. Reconciling these theories requires understanding how quantum effects might affect the geometry of space and time itself. If light were stopped, would this quantum gravitational connection be severed, allowing space-time to exist independently of quantum phenomena? As we probe deeper into the quantum realm, we discover that light is not merely electromagnetic radiation, but the foundation of electromagnetic force, the mediator of atomic structure, and the carrier of quantum information. The question of whether time could exist without light becomes a question about the fundamental nature of reality itself. Would stopping light eliminate the quantum processes that might be responsible for the flow of time? Or would we discover that time emerges from even deeper principles that operate independently of all known forces and particles? At the quantum level, light and time are inseparable. But what would happen if light's flow were halted? Would time too cease to flow? Or would the universe find ways to continue its quantum dance in forms we cannot yet imagine, revealing aspects of reality that remain hidden as long as photons carry information through the quantum vacuum? Imagine for a moment that you possess the power to stop light throughout the entire universe, not merely to block it or absorb it, but to bring every photon to a complete standstill, freezing electromagnetic radiation in place wherever it happened to be at the moment of cessation. This thought experiment pushes the boundaries of physics and imagination, allowing us to explore what might happen if the cosmic speed limit were suddenly reduced to zero, if the fundamental constant that governs causality itself could be altered at will. The moment of stopping would be unlike anything ever experienced in the history of the universe. Every photon traveling through space, from the ancient light of the cosmic microwave background to the fresh radiation streaming from nearby stars, would suddenly freeze in place. The night sky, normally illuminated by starlight that has traveled for years or millennia to reach us, would display a three-dimensional tableau of frozen light rays suspended in the void, like cosmic sculptures made of pure energy. Consider what this frozen universe of light would look like to an observer who could somehow still see without the normal process of photons entering their eyes. Sunlight, normally an invisible stream of particles racing toward Earth at 300 million meters per second, would become visible as a vast river of golden energy stretching from our star to our planet. The familiar 8-minute delay between events on the Sun and their observation on Earth would be made manifest as a highway of light spanning 150 million kilometers of space. Radio waves from distant galaxies, normally undetectable without specialized instruments, might become visible as gossamer threads stretching across cosmic distances. The familiar constellations, would be connected by visible trails of light, showing the actual paths that starlight follows through space. The universe would reveal its hidden electromagnetic skeleton, the vast network of light rays that normally races invisibly through the cosmos, carrying information between all points in space. But the implications extend far beyond the merely visual. If stopping light affected only photons traveling through empty space while leaving local electromagnetic phenomena intact, the consequences would still be dramatic. All long-distance communication would cease instantly. Radio signals could no longer travel between continents, satellite communications would fail, and the internet would fragment into isolated local networks. Humanity would be cut off from space-based observations, unable to receive data from telescopes in orbit or signals from interplanetary probes. The loss of sunlight would have immediate and catastrophic effects on Earth's climate and ecosystems. Plants would cease photosynthesis within hours, beginning a cascade of biological collapse that would ripple through every food chain on the planet. The solar energy that drives weather patterns would stop arriving, causing atmospheric circulation to gradually slow and eventually halt. Without the steady input of solar radiation, Earth's surface would begin cooling toward the frigid temperatures of deep space. Yet these consequences assume that only photons traveling through vacuum would be affected. If stopping light also eliminated the virtual photons that mediate electromagnetic forces, the effects would be far more profound and immediate. The electromagnetic force is responsible for holding electrons in their atomic orbitals, creating the chemical bonds between atoms and enabling all the electrical processes that power living organisms. Without virtual photons to carry electromagnetic force, matter itself might begin to disintegrate. Atomic nuclei would retain their protons and neutrons, held together by the strong nuclear force, but electrons would no longer be electromagnetically bound to these nuclei. Atoms would dissolve into seas of unbound nuclei surrounded by clouds of free electrons. All chemical bonds would break simultaneously, reducing complex molecules to their constituent atoms. The intricate molecular machinery of life, from DNA to proteins to cell membranes, would collapse into atomic soup. The human body, like all living things, depends on electrical signals for its operation. Neural activity, muscle contraction, and even the basic maintenance of cellular integrity all require the flow of electrical currents mediated by virtual photons. If these electromagnetic processes ceased, consciousness would vanish instantly as neural networks fell silent. Life itself would end not with a bang, but with the sudden cessation of the electrical symphony that animates all biological systems. But perhaps stopping light would affect only real photons, while leaving virtual photons intact. In this scenario, electromagnetic forces would continue to operate at the atomic level, preserving the structure of matter and the possibility of life. However, the inability of electromagnetic radiation to propagate through space would still have profound consequences for the universe as a whole. Stars would continue their nuclear fusion reactions, converting hydrogen to helium and releasing enormous amounts of energy. But this energy, normally carried away by photons, would have nowhere to go. The radiation pressure that normally balances gravitational collapse in stellar cores would disappear, causing stars to begin contracting under their own gravity. This contraction would heat the stellar cores, accelerating fusion reactions and creating a runaway process that might cause most stars to explode as supernovae within days or weeks. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, would suddenly freeze in place. This ancient light, which has been cooling and redshifting for nearly 14 billion years as the universe expanded, would stop evolving. The expansion of the universe might continue, but we would lose our primary means of studying cosmic evolution and measuring the universe's fundamental properties. Black holes would undergo dramatic changes if photons could no longer escape their vicinity. Hawking radiation, the quantum process by which black holes slowly evaporate, depends on the emission of photons from near the event horizon. If this radiation were halted, black holes would become truly eternal, unable to return their captured mass and energy to the universe. The information paradox associated with black hole evaporation would be resolved in the most dramatic way possible, with information permanently trapped behind event horizons. The propagation of gravitational waves might also be affected if stopping light altered the fundamental structure of space-time. These ripples in the fabric of space and time travel at light speed and carry information about cosmic events like black hole mergers and neutron star collisions. If gravitational waves could no longer propagate, different regions of the universe would become gravitationally isolated, unable to influence each other through changes in space-time curvature. Quantum mechanics would face a crisis if photons could no longer carry information between quantum systems. Quantum entanglement, which creates instantaneous correlations between distant particles, might persist since it does not actually transmit information faster than light. But the process of quantum measurement, which typically involves photons carrying information from quantum systems to measurement devices, would become impossible. Quantum systems might remain forever in superposition, unable to collapse into definite states. The arrow of time itself might be affected by stopping light. The second law of thermodynamics, which states that entropy always increases, depends on the ability of energy and information to flow from organized to disorganized states. Light plays a crucial role in this process, carrying energy away from hot objects and distributing it throughout space. Without photons to mediate energy transfer, would entropy increase cease? Would the universe freeze not just electromagnetically but thermodynamically as well? Consider the implications for causality and the logical structure of reality. The principle that cause must precede effect depends on the cosmic speed limit set by light. If information could not propagate faster than light, then events could be ordered in a logical sequence where causes always preceded their effects. But if light speed became zero, information could not propagate at all, breaking the causal connections that give structure to physical law. Each region of space would become isolated in its own causal bubble, unable to influence or be influenced by events elsewhere. The universe would fragment into countless disconnected domains, each evolving independently without any possibility of coordination or interaction. The unified cosmos we observe today might dissolve into a collection of isolated islands of existence, each following its own independent timeline. The expansion of the universe presents another puzzle in a cosmos where light has been stopped. Current observations show that space itself is expanding, carrying distant galaxies away from us at ever-increasing speeds. This expansion is driven by dark energy, a mysterious force that comprises about 70% of the universe's total energy density. If light could no longer propagate, we would lose our ability to observe this expansion directly, but the process might continue nonetheless. Space might continue to expand, even as the light that would normally carry information about this expansion remained frozen in place. New regions of space-time would come into existence, but they would be forever cut off from communication with existing regions. The observable universe would become truly finite, bounded not by the speed of light and the age of the cosmos, but by the distance that light had traveled before being stopped. Quantum field theory describes empty space as filled with quantum fluctuations, virtual particles that pop in and out of existence at the smallest scales of space and time. These fluctuations include virtual photon pairs that contribute to the quantum vacuum energy and affect the behavior of charged particles. If stopping light eliminated these quantum fluctuations, the very nature of empty space would change, potentially altering fundamental constants and the basic properties of matter. The Casimir effect, which creates measurable forces between closely spaced conducting plates due to quantum vacuum fluctuations, might disappear if virtual photons cease to exist. This would provide a direct experimental test of whether stopping light affects only real photons or extends to the virtual particles that mediate fundamental forces. The elimination of vacuum fluctuations might also affect the stability of particle masses and the values of physical constants. Time travel paradoxes, normally prevented by the cosmic speed limit, might become possible in a universe where light could not propagate. The chronology protection conjecture suggests that the laws of physics conspire to prevent closed time-like curves that would allow travel into the past. But if causality could not propagate through space, would temporal paradoxes become possible? Could events influence their own past causes in ways that would tear apart the logical fabric of reality? The concept of simultaneity, already shown by relativity to be observer-dependent, would become even more problematic in a lightless universe. Without light signals to synchronize clocks across space, there would be no way to establish what events are happening now at distant locations. Each point in space would exist in its own private present moment, with no connection to the temporal experience of other regions. Perhaps most profoundly, stopping light might reveal whether time itself is fundamental or emergent. If time depends on the propagation of information and the evolution of quantum states, then halting light might cause time to freeze along with electromagnetic radiation. Alternatively, if time emerges from deeper principles that operate independently of known forces, it might continue to flow in ways we cannot currently imagine, creating forms of temporal experience that transcend our current understanding. The thought experiment of stopping light pushes us to examine the deepest assumptions about reality, time, and existence itself. It reveals how intimately connected light is to every aspect of the universe we know, from the smallest quantum interactions to the largest cosmic structures. In contemplating this impossible scenario, we gain new appreciation for the elegant unity that connects electromagnetic radiation, temporal flow, and the rich complexity of existence. Stopping light may sound impossible, but in a universe of infinite possibilities, what would happen if we could halt the passage of light? Would this act freeze all motion, from atomic particles to the expansion of the universe? Or would we discover that reality has hidden depths that allow existence to continue, even when the cosmic messenger falls silent? While we have explored the theoretical implications of stopping light throughout the universe, the question remains whether such a feat is actually possible within the known laws of physics. Scientists have made remarkable progress in controlling and manipulating light in ways that would have seemed impossible just decades ago. From slowing light to a crawl to temporarily stopping it altogether in specialized materials, researchers have pushed the boundaries of what can be achieved with electromagnetic radiation. Yet the gulf between these laboratory achievements and the cosmic scenario we have been contemplating remains vast. The first successful attempts to slow light dramatically occurred in the late 1990s, when researchers at Harvard University managed to reduce light speed from its normal 300 million meters per second to just 17 meters per second. This extraordinary feat was accomplished using a technique called electromagnetically induced transparency in a cloud of ultra-cold sodium atoms. By precisely tuning laser beams to create quantum interference effects, the scientists were able to make the atomic medium nearly transparent to specific frequencies of light, while dramatically altering its refractive properties. The physics behind light slowing involves the interaction between photons and matter at the quantum level. When light enters a material, it interacts with the electrons in atoms, causing them to oscillate and re-emit electromagnetic radiation. In most materials, this process results in only a modest reduction in light speed, creating the refractive index that bends light as it passes through glass or water. But in specially prepared quantum systems, these interactions can be enhanced to create dramatic effects. Electromagnetically induced transparency relies on quantum interference between different energy pathways that photons can take through the atomic medium. By carefully controlling additional laser beams, scientists can create conditions where destructive interference cancels out most absorption, while constructive interference enhances the dispersive effects that slow light propagation. The result is a medium that is nearly transparent to light but has optical properties unlike anything found in nature. Building on these early experiments, researchers achieved even more dramatic results by bringing light to a complete stop within atomic vapors. In these experiments, a light pulse is first slowed dramatically as it enters the atomic medium, then trapped by turning off the control laser that creates the transparency conditions. The trapped light pulse can be stored in the atomic system for microseconds or even milliseconds before being released by turning the control laser back on. During the storage period, the light technically no longer exists as electromagnetic radiation, but is converted into atomic coherences, quantum mechanical states, where the atoms collectively store the information that was carried by the original light pulse. When the light is released, the stored atomic coherences convert back into photons, recreating the original pulse with remarkable fidelity. This process demonstrates that light can indeed be stopped, at least temporarily, and in highly controlled conditions. The practical applications of these light control techniques are already being explored in quantum computing and quantum communication systems. Quantum memories that can store and retrieve individual photons are essential components for quantum networks that could eventually connect quantum computers across vast distances. The ability to stop light provides a way to synchronize quantum operations and to buffer quantum information during processing. However, these laboratory demonstrations of stopped light operate under extremely restrictive conditions that would be impossible to replicate on a cosmic scale. The atomic vapors used in these experiments must be cooled to temperatures just billionths of a degree, above absolute zero, and maintained in near-perfect vacuum conditions. The entire system must be isolated from any disturbances that could disrupt the delicate quantum states required for light storage. The energy requirements for extending these techniques beyond the laboratory scale become prohibitive very quickly. Cooling even a kilogram of atoms to the temperatures required for electromagnetically induced transparency would require more energy than humanity produces in a year. Scaling up to cosmic dimensions would require energy resources that dwarf the total output of all stars in the observable universe by countless orders of magnitude. Moreover, the light-stopping techniques demonstrated in laboratories work only for very specific frequencies and only within the confines of the prepared atomic medium. Light at other frequencies passes through the system normally, and light outside the medium continues to propagate at normal speeds. There is no known mechanism that could simultaneously affect all electromagnetic radiation throughout space. Alternative approaches to light manipulation have been explored using metamaterials, artificially engineered structures with optical properties not found in natural materials. These metamaterials can bend light in unusual ways, create regions of negative refractive index, and even render objects invisible at specific frequencies. Some theoretical designs could slow light significantly or trap it in complex resonance structures. Photonic crystals, materials with periodic variations in refractive index, can create photonic band gaps that completely prohibit the propagation of light at certain frequencies. Within these band gaps, photons cannot propagate regardless of their direction or intensity, effectively creating regions where specific colors of light cannot exist. While this represents a form of light stopping, it affects only narrow frequency ranges and requires materials with precisely engineered structures at the wavelength scale of light. Plasmonic structures, which confine light to the surfaces of metallic nanoparticles, can slow light propagation and enhance interactions between light and matter. Surface plasmons, collective oscillations of electrons at metal interfaces, can trap light in regions much smaller than the wavelength, creating extremely high field intensities. These effects have potential applications in sensing and solar energy harvesting, but do not represent true stopping of light. The concept of a perfect absorber, a material that absorbs 100% of incident light without reflection, has been realized in certain metamaterial structures. These perfect absorbers convert light energy into heat with perfect efficiency, effectively removing photons from the electromagnetic field. While this eliminates light within the absorbing material, it does not stop light propagation, but rather destroys the photons entirely. Quantum mechanical considerations impose fundamental limits on any attempt to stop light universally. The uncertainty principle relates energy and time, suggesting that stopping electromagnetic radiation completely would require infinite precision in energy measurement, which is impossible according to quantum mechanics. Virtual photons, which mediate electromagnetic forces, exist for such brief periods that they cannot be directly observed or controlled using conventional techniques. The vacuum itself presents challenges for any universal light-stopping mechanism. Quantum field theory describes the vacuum as filled with fluctuations that constantly create and annihilate virtual particle pairs. These vacuum fluctuations are fundamental features of spacetime itself and cannot be eliminated without altering the basic structure of reality. Any technology capable of stopping virtual photons would need to modify the quantum vacuum, requiring manipulations of spacetime at the Planck scale. Gravitational effects also constrain the possibility of stopping light. Einstein's general relativity shows that electromagnetic radiation carries energy and momentum that contribute to the curvature of spacetime. Eliminating all electromagnetic energy from the universe would alter the gravitational field of every object, potentially disrupting planetary orbits, stellar structure, and the large-scale evolution of the cosmos. The cosmic microwave background radiation presents a particular challenge for any light-stopping technology. This ancient light fills all of space and represents the afterglow of the Big Bang itself. Stopping this radiation would require reaching every point in the observable universe simultaneously, a task that seems impossible given the finite speed of any intervention and the ongoing expansion of space. Theoretical approaches to universal light stopping might involve modifications to the fundamental constants of nature. If the fine structure constant, which determines the strength of electromagnetic interactions, could be adjusted to zero, electromagnetic forces would disappear throughout the universe. However, changing fundamental constants would likely require manipulating the quantum fields from which they emerge, a technology far beyond any conceivable future capability. Another theoretical approach might involve creating a universe-wide field that interferes destructively with all electromagnetic radiation. Such a field would need to have exactly the right phase and amplitude to cancel all possible photon states simultaneously, a requirement that seems mathematically impossible given the infinite variety of electromagnetic radiation present in the universe. The holographic principle in physics suggests that all information contained within a volume of space can be encoded on its boundary surface. If this principle is correct, then stopping light within a volume might require controlling the holographic information on its boundary, which could involve manipulating quantum entanglement networks that span cosmic distances. Wormhole technology, if it ever becomes possible, might theoretically allow interventions that could affect light throughout the universe simultaneously. By creating shortcuts through space-time, it might be possible to reach all regions of the cosmos instantaneously and implement light-stopping mechanisms everywhere at once. However, wormholes remain highly speculative and might not be stable enough to support such operations. Time travel, another theoretical possibility, might allow retroactive implementation of light-stopping conditions. By traveling back to the early universe and altering the initial conditions of cosmic evolution, it might be possible to create a universe where light never existed, or where electromagnetic forces operate differently. However, time travel paradoxes and chronology protection mechanisms might prevent such alterations from being possible. Advanced civilizations with technology millions or billions of years beyond our current capabilities might develop techniques for manipulating space-time and quantum fields in ways we cannot currently imagine. Such civilizations might have discovered principles of physics that allow control over fundamental forces and constants, making universal light stopping theoretically achievable within their technological framework. The energy scales involved in universal light stopping suggest that only cosmic-scale technologies could attempt such a feat. Dyson spheres that capture the entire energy output of stars, black hole energy extraction systems that tap the rotational energy of spinning black holes, or matter-antimatter annihilation reactors that convert mass to energy with perfect efficiency might provide the power needed for cosmic-scale manipulations. Yet even with unlimited energy resources, the fundamental physics constraints remain formidable. The speed of light limitation means that any intervention would take billions of years to reach the most distant parts of the observable universe. By the time the intervention arrived, cosmic expansion would have created new regions of space beyond its reach. Quantum non-locality and entanglement might provide a workaround for the speed of light limitation. If quantum entangled systems could be distributed throughout the universe, it might be possible to create simultaneous effects across cosmic distances without violating causality. However, quantum entanglement cannot transmit information or energy faster than light, limiting its utility for practical interventions. The multiverse concept suggests that our universe might be one of infinitely many parallel realities with different physical laws. In some of these parallel universes, electromagnetic forces might be absent or operate differently, creating naturally occurring examples of cosmos without light. Studying such universes, if they exist and if they could be observed, might provide insights into whether time can exist independently of electromagnetic phenomena. String theory and other theories of quantum gravity suggest that the familiar forces and particles we observe might be low-energy manifestations of more fundamental structures operating at the Planck scale. These theories hint at the possibility that electromagnetic forces could be switched off by manipulating the underlying geometric structures of space-time, though such manipulations would require technology operating at energy scales comparable to the Big Bang itself. As we examine the practical challenges of stopping light, we discover that while laboratory demonstrations show remarkable control over electromagnetic radiation under specific conditions, the leap to universal light stopping remains beyond the boundaries of known physics and conceivable technology. The universe seems to be structured in ways that preserve the fundamental role of light in mediating forces, carrying information, and maintaining the causal structure of reality. While we cannot yet stop light entirely, advances in technology allow us to manipulate it in ways we once thought impossible. What would it mean if we could one day stop it completely? And what new physics might we need to discover to make such cosmic manipulations possible? The pursuit of these questions continues to push the boundaries of our understanding and might someday reveal whether the universe holds deeper secrets that could allow us to rewrite the fundamental rules of existence itself. Our exploration of light and its relationship to time has revealed profound insights about the nature of reality itself. As we stand at the intersection of established physics and speculative possibility, we find ourselves confronting questions that challenge our most basic assumptions about existence, causality, and the flow of temporal experience. The theoretical framework that emerges from considering what would happen if light could be stopped illuminates not just the role of electromagnetic radiation in our universe, but the deeper mysteries of time itself. The relationship between light and time appears to be far more fundamental than early physicists ever imagined. When Newton conceived of absolute time flowing uniformly throughout the universe, independent of matter and motion, He could not have anticipated that light would prove to be the thread connecting space and time into a unified fabric. Einstein's revelation that the speed of light represents the maximum rate at which causality can propagate through space showed us that time is not a universal constant, but a flexible dimension whose flow depends on motion and gravity. Yet our thought experiment of stopping light suggests an even deeper connection. If electromagnetic radiation could be halted throughout the universe, the consequences would cascade through every level of physical reality, from the quantum mechanical processes that govern atomic behavior to the cosmic expansion that shapes the evolution of space itself. This suggests that light is not merely fast-moving energy, but a fundamental component of the mechanism by which time flows forward and change propagates through the cosmos. Quantum mechanics has revealed that time at the microscopic level operates differently than our everyday experience suggests. Rather than flowing smoothly like a river, quantum time seems to evolve in discrete steps, with each quantum measurement representing a kind of temporal tick that advances the universe from one state to the next. The role of photons in quantum measurements, carrying information from quantum systems to measurement devices, hints that light might be essential to this quantum evolution of time. If light were stopped and quantum measurements could no longer occur, quantum systems might remain frozen in superposition states, unable to collapse into the definite realities that allow time to advance. This raises the profound possibility that the flow of time itself depends on the constant dance of quantum measurements mediated by electromagnetic radiation. Without light to carry information about quantum states, time might lose its forward direction, creating a universe where past, present, and future become meaningless distinctions. The arrow of time, the fact that temporal flow moves from past to future rather than the reverse, has long puzzled physicists and philosophers. The fundamental laws of physics are mostly time reversible, showing no preference for forward versus backward temporal evolution. Yet we observe a clear direction to time, with entropy increasing, information spreading from organized to disorganized states, and cause always preceding effect. The role of light in carrying information away from organized systems and distributing it throughout space suggests that electromagnetic radiation might be responsible for time's arrow. If light could be stopped, would this directional flow of information cease, causing the arrow of time to disappear? Would the universe become temporally symmetric, with forward and backward time becoming equally probable? Such a scenario might create a reality where effects could precede their causes, where complex structures could spontaneously assemble from chaos, and where the logical framework that makes existence comprehensible would dissolve. String theory and other approaches to quantum gravity suggest that space and time might not be fundamental but emergent properties of deeper structures. In these theories, the familiar dimensions we experience arise from the complex interactions of tiny vibrating strings or other exotic objects operating at scales far smaller than atomic nuclei. If this picture is correct, then the relationship between light and time might reflect even more fundamental connections operating at the Planck scale. Some string theories predict the existence of extraspatial dimensions beyond the three we normally experience. These additional dimensions might be compactified or hidden in ways that make them undetectable at normal energy scales. The propagation of light through these extra dimensions could affect the flow of time in our familiar three-dimensional space. Stopping light might reveal these hidden dimensions or alter their relationship to temporal flow in ways that could fundamentally change the structure of reality. The holographic principle, which suggests that all information in a volume of space can be encoded on its boundary surface, implies a deep connection between information, space, and time. In this view, three-dimensional reality might be a projection of two-dimensional information, with the flow of time corresponding to the evolution of this boundary-encoded data. Light, as the primary carrier of information through space, might play a crucial role in maintaining the holographic projection that creates our experienced reality. If light were stopped and information could no longer flow between different regions of space, would the holographic projection collapse? Would three-dimensional space reduce to its two-dimensional boundary encoding, creating a fundamentally different kind of universe where spatial extension becomes illusory? The implications for consciousness and existence in such a reality are difficult to imagine, suggesting forms of experience that transcend our current understanding. Loop quantum gravity, an alternative approach to unifying quantum mechanics with general relativity, proposes that space and time are quantized at the smallest scales. In this theory, space consists of discrete units connected in a network structure, with time evolving through discrete steps as this network changes configuration. The quantum of time, if it exists, might be related to the time required for light to cross one quantum of space, creating a fundamental connection between electromagnetic propagation and temporal flow. If light could be stopped in a loop quantum gravity universe, would the discrete evolution of the space network halt as well? Would time freeze at whatever quantum temporal step it had reached, creating a universe where the network of space remained locked in a single configuration for eternity? Alternatively, might the network continue to evolve through non-electromagnetic processes, revealing that time has quantum mechanical aspects independent of light propagation? The many worlds interpretation of quantum mechanics suggests that every quantum measurement causes the universe to split into multiple parallel realities, each corresponding to a different measurement outcome. In this view, time becomes the dimension along which these parallel universes branch and proliferate. The role of photons in quantum measurements suggests that light might be essential to this branching process, with each photon detection creating new parallel worlds. If light was stopped and quantum measurements could no longer occur, would the branching of parallel universes cease? Would the multiverse freeze into its current configuration, unable to create new realities as quantum systems remained locked in superposition? This scenario might preserve all existing parallel worlds while preventing the creation of new ones, resulting in a static multiverse where possibilities become fixed rather than constantly multiplying. Consciousness presents perhaps the deepest mystery in considering the relationship between light and time. Human awareness seems to require the constant flow of time to create the stream of experience that constitutes conscious existence. The electrical processes in the brain that give rise to consciousness depend on electromagnetic forces mediated by virtual photons. If light were stopped and these forces ceased to operate, would consciousness disappear entirely, or would it reveal aspects of awareness that operate independently of electromagnetic phenomena? Some theories propose that consciousness might be a fundamental feature of the universe rather than an emergent property of complex information processing. In these panpsychist views, even elementary particles might possess primitive forms of awareness that combine to create higher-level consciousness in complex systems. If consciousness is fundamental, it might persist even in a universe where light has been stopped, creating forms of awareness that operate independently of electromagnetic processes. The measurement problem in quantum mechanics takes on new significance when considering consciousness and time. Some interpretations suggest that conscious observation plays a role in collapsing quantum wave functions and determining which quantum outcomes become real. If consciousness depends on electromagnetic processes that would cease if light were stopped, would quantum collapse become impossible? Would the universe remain locked in a state of pure quantum potential, with no conscious observers to select which possibilities become actual? Alternatively, consciousness might reveal itself to be more fundamental than electromagnetic phenomena, capable of causing quantum collapse even in the absence of light. This would suggest that awareness represents a basic feature of reality that operates independently of known physical forces, with implications that could revolutionize our understanding of both consciousness and physics. The cosmological implications of stopping light extend beyond the observable universe to questions about the nature of space and time on the largest scales. Current observations suggest that space itself is expanding at an accelerating rate, driven by dark energy that comprises about 70% of the universe's total energy content. This expansion carries distant galaxies away from us, at speeds that approach light speed at the edge of the observable universe. If light were stopped, but cosmic expansion continued, new regions of space-time would come into existence without any possibility of communication with existing regions. The universe would fragment into isolated domains, each cut off from all others and unable to influence or be influenced by events elsewhere. Time might continue to flow within each domain, while losing all connection to temporal flow in other regions. This fragmentation raises questions about whether time is a global property of the universe or a local feature that can exist independently in different regions. If time is global, stopping light might halt temporal flow everywhere simultaneously. If time is local, different regions might develop their own unique temporal rhythms, creating a cosmos where the unified flow of time dissolves into countless private temporal experiences. The concept of eternal inflation in cosmology suggests that new universes are constantly being created through quantum fluctuations in the inflating space-time of a parent universe. This process creates an infinite multiverse, where every possible combination of physical laws and initial conditions is realized somewhere. In such a multiverse, universes where light has different properties or where electromagnetic forces operate differently would naturally exist. Studying these variant universes, if they could be observed, might provide insights into how time behaves in the absence of familiar electromagnetic phenomena. Some universes might have time flowing at different rates. Others might have multiple temporal dimensions. And still others might lack time entirely, while supporting forms of existence that transcend temporal flow. The anthropic principle, which observes that the physical constants of our universe seem finely tuned to allow the existence of complexity and life, takes on new meaning when considering light and time. The speed of light, the strength of electromagnetic forces, and the quantum mechanical properties of photons all fall within narrow ranges that permit the formation of atoms, molecules, and the complex chemistry required for life. If any of these parameters were significantly different, the universe might be unable to support the organized structures that give rise to consciousness and the experience of temporal flow. This suggests that there might be deep connections between the values of physical constants, the possibility of complex organization, and the nature of time itself. Stopping light might reveal whether these connections are accidental or whether they reflect fundamental principles that govern the structure of possible realities. As theoretical physics pushes toward a theory of everything that would unify all fundamental forces and explain the deepest laws of nature, the relationship between light and time provides crucial clues about what such a theory might reveal. The intimate connections we have discovered between electromagnetic radiation, quantum mechanics, space-time geometry, and temporal flow suggest that any complete understanding of reality must account for these relationships. The possibility of stopping light, however remote, serves as a thought experiment that illuminates the hidden assumptions underlying our current understanding of physics. It reveals how deeply electromagnetic phenomena are woven into the fabric of existence and suggests that light might be more than just one form of energy among many. Instead, electromagnetic radiation appears to be a fundamental component of the mechanism by which reality maintains its coherence. Causality preserves its logical structure, and time flows forward rather than remaining frozen in an eternal present. Whether stopping light would truly freeze time or would reveal deeper temporal structures operating independently of electromagnetic phenomena remains an open question that pushes the boundaries of both physics and philosophy. The answer might require discoveries that revolutionize our understanding of space, time, matter, energy, and consciousness itself, revealing aspects of reality that remain hidden as long as light races through the cosmos at its cosmic speed limit. The relationship between light and time is still a profound mystery. Could stopping light be the key to unlocking new realms of physics and understanding the true nature of time? Or would we discover that time emerges from principles so fundamental that they transcend all known forces and phenomena? The pursuit of these questions continues to drive theoretical physics toward deeper understanding of the cosmos and our place within the infinite mystery of existence. As our journey through the mysteries of light and time draws to a close, we find ourselves standing at the edge of an infinite ocean of questions, each wave bringing new wonders and deeper puzzles about the nature of existence itself. We began with a simple question: if you could stop light, would you freeze time? But our exploration has revealed that this question touches the very heart of reality, challenging our understanding of space, time, matter, energy, consciousness, and the fundamental laws that govern everything we know. Light, we have discovered, is far more than the electromagnetic radiation that illuminates our world and carries information across cosmic distances. It is the cosmic speed limit that sets the boundary between possible and impossible, the mediator of electromagnetic forces that hold atoms together, the carrier of quantum information that allows measurement and observation, and perhaps even the fundamental mechanism by which time flows forward rather than remaining frozen in an eternal present. In contemplating what would happen if light could be stopped, we have glimpsed the intricate web of connections that bind together every aspect of our universe. From the quantum mechanical processes that govern atomic behavior to the cosmic expansion that shapes the evolution of space itself, light appears to be woven into the very fabric of existence in ways that make its complete absence almost unimaginable. Yet the possibility, however remote, of stopping light has served as a powerful lens through which to examine the hidden assumptions underlying our understanding of physics. It has revealed how deeply electromagnetic phenomena penetrate into every corner of reality, and has suggested that our familiar world might be just one possibility among countless others. A universe where the cosmic constants happen to have values that permit the existence of complexity, consciousness, and the rich tapestry of phenomena we observe. The relationship between light and time has emerged as one of the most profound mysteries in all of physics. Time dilation effects show us that the flow of time depends on motion through space and the strength of gravitational fields. The quantum measurement problem suggests that time might advance through discrete steps as wave functions collapse and possibilities become actualities. The arrow of time reveals that temporal flow has a direction that might depend on the propagation of information and the increase of entropy throughout the cosmos. If light could be stopped, all of these temporal phenomena might be affected in ways that cascade through every level of physical reality. Quantum systems might remain frozen in superposition, unable to collapse into the definite states that allow time to advance. Information could no longer flow between different regions of space, causing the universe to fragment into isolated domains where cause and effect become meaningless. The arrow of time might disappear, creating a reality where forward and backward temporal flow become equally probable. Yet perhaps most remarkably, our exploration has revealed that consciousness itself might be intimately connected to the flow of light and time. The electrical processes in the brain that give rise to awareness depend on electromagnetic forces mediated by virtual photons. The stream of visual experience that shapes our perception of temporal flow requires the constant arrival of light signals carrying information about the changing world around us. If light was stopped, consciousness might vanish entirely, or it might reveal aspects of awareness that operate independently of electromagnetic phenomena. The quantum nature of light has shown us a reality far stranger than our everyday experience suggests. Wave-particle duality reveals that photons exist in superposition states until observed, behaving as both waves and particles depending on how we choose to measure them. Quantum entanglement creates correlations between distant particles that seem to transcend the speed of light limitation, suggesting that the universe contains hidden connections that operate outside the normal flow of electromagnetic radiation. Virtual photons that mediate electromagnetic forces exist for impossibly brief moments, popping in and out of the quantum vacuum in a constant dance of creation and annihilation. These quantum fluctuations might be essential to the structure of space and time themselves, creating the foundation upon which all larger-scale phenomena are built. If light were stopped, and these fluctuations ceased, the very nature of empty space might change, altering fundamental constants and the basic properties of matter. Black holes have provided crucial insights into the extreme relationship between light, gravity, and time. At the event horizon, the boundary where light can no longer escape, time appears to stop from the perspective of outside observers while continuing to flow normally for anyone falling in. This paradox reveals the relative nature of temporal flow and suggests that time might have aspects that operate independently of electromagnetic phenomena. The cosmic scale implications of stopping light extend beyond our observable universe to questions about the nature of space and time on the larger scales. If the cosmic microwave background radiation were frozen in place, we would lose our primary window into the early universe and the evolution of cosmic structure. If gravitational waves could no longer propagate, different regions of space-time would become isolated, unable to influence each other through changes in geometry. Yet perhaps the most profound revelation from our exploration is that the universe might contain forms of time and existence that transcend our current understanding. String theory suggests that familiar dimensions might emerge from deeper structures, operating at scales far smaller than anything we can currently observe. The holographic principle hints that three-dimensional reality might be a projection of two-dimensional information. Loop quantum gravity proposes that space and time themselves might be quantized, evolving through discrete steps rather than flowing continuously. These theoretical frameworks suggest that the relationship between light and time might reflect even more fundamental connections operating at the deepest levels of reality. If electromagnetic radiation could somehow be stopped throughout the universe, we might discover that time has hidden depths that allow it to flow through mechanisms we have not yet imagined. Alternatively, we might find that light is so essential to the structure of existence that its absence would cause reality itself to collapse into forms that bear no resemblance to anything we can currently comprehend. The practical challenges of actually stopping light have shown us the vast gulf between laboratory demonstrations and cosmic scale interventions. While scientists have achieved remarkable control over electromagnetic radiation under highly specialized conditions, extending these techniques to universal scales would require energy resources and technological capabilities that far exceed anything conceivable with known physics. Yet the pursuit of these seemingly impossible goals continues to drive scientific discovery and might someday reveal new principles that could revolutionize our understanding of space, time, and existence itself. As we contemplate the infinite mystery of light and time, we are reminded that every answer we discover reveals new questions that probe even deeper into the nature of reality. The universe appears to be constructed in layers of mystery, each more profound than the last, extending from the quantum mechanical realm where particles exist in multiple states simultaneously, to the cosmic scale where space itself expands and carries galaxies apart at ever-increasing speeds. Our exploration has revealed that we live in a cosmos of almost unimaginable complexity and beauty, where the simplest phenomena connect to the deepest principles governing existence. Light, racing through space at its cosmic speed limit, carries more than just energy and information. It carries the very structure of causality, the mechanism of temporal flow, and perhaps even the foundation of consciousness itself. The question of whether stopping light would freeze time remains tantalizingly open, pointing toward discoveries that might revolutionize physics and philosophy alike. The answer might require understanding quantum gravity, consciousness, the nature of information, and the deepest laws governing space and time. It might involve principles we have not yet discovered, phenomena we have not yet observed, and forms of existence we have not yet imagined. Perhaps most beautifully, our journey has shown us that the universe is not a collection of separate objects moving through empty space and time, but a unified whole where every part connects to every other part through relationships of stunning elegance and complexity. Light serves as one of the primary messengers in this cosmic web of connection, carrying information about distant events, mediating forces between particles, and perhaps even creating the temporal flow that allows change and evolution to occur. As we rest beneath the stars, knowing that the light reaching our eyes left those distant suns years or centuries ago, we are witnessing the universe as it was in the past, while simultaneously participating in its present moment evolution. We are conscious beings made of star stuff, able to contemplate our own existence and to ask questions about the deepest nature of reality. In pursuing these questions, we are participating in the universe's ongoing journey of self-discovery, contributing to the cosmic awakening of consciousness that might be the ultimate purpose of existence itself. The infinite mystery of light and time stretches before us like an endless ocean, with each new discovery revealing vast new territories to explore. Whether light is fundamental or emergent, whether time flows or simply is, whether consciousness creates reality or emerges from it, these questions continue to beckon us toward deeper understanding and greater wonder. Light is both a messenger and a boundary, shaping our understanding of the universe while simultaneously limiting what we can know about distant events and future possibilities. Time flows forward, carrying us from past to future, while hiding the mechanisms by which this flow is generated and sustained. Together, light and time create the stage upon which the cosmic drama of existence unfolds, from the dance of subatomic particles to the birth and death of stars, from the evolution of life to the awakening of consciousness. In the end, our exploration of whether stopping light would freeze time has revealed not just the intimate connection between electromagnetic radiation and temporal flow, but the profound mystery of existence itself. We are part of a universe that appears to be simultaneously comprehensible and inexhaustible, where every answered question opens doorways to deeper mysteries that continue to beckon us forward into the infinite unknown. Light is both a messenger and a boundary, shaping our understanding of the universe. While we cannot yet stop light, the pursuit of knowledge continues, and with it, the possibility that one day we may unlock the mysteries of time itself. Rest now beneath the stars, knowing that the answers we seek are always just beyond the horizon, waiting to be discovered by curious minds willing to venture into the infinite mystery of existence.